Welcome, everyone. I'm so glad to see such a full room. It's awesome. Thanks for being here. My name's Wes Lauer. I'm a professor in civil and environmental engineering. So I'm really excited to introduce the teams that will be presenting this afternoon. So this is the culmination of an awful lot of work for the students and their faculty advisors and their external sponsors. So please join me now in giving a round of applause for all of that work. So the order of events, we have 3 sessions this afternoon. The first one is the session for the civil engineering teams. After that, we have a session for an environmental science team and 2 data science teams. Those projects, at least 2 of them relate to water, and I think they make sense to be lumped together. And then there's a 3rd presentation in this room after that, so the 3rd session, and there's also a project that relates to environmental science in that session. So for those of you who are here to see civil and environmental engineering related projects, just know that there's a presentation in this room at the beginning of each session that relates to that. But I think the data science projects relate to those topics too. So I hope you can join us in here for each of those. So without any further ado, I'd like to introduce the first civil and environmental engineering team. This is CEE team 14.1. And I'd like to invite you up to give your presentation. And in the interest of time, we'll let the students introduce themselves, and there'll be a short 5-minute Q&A session or so between talks. So welcome.
Oh.
Check.
Check. This one? That one doesn't. I think it's this one. No, turn it on. Okay.
Yeah, that's been that.
Oh.
Oh, okay. We only have one clicker.
Turn it on. It's on.
I can advance.
I can use the key.
Well, you need to present. You can't just click here and you'll present.
That's the one it's on.
Hello, everyone. We're Senior Design Team CEE 24.1, and today we're presenting on the SeaTac Airport home plate parking lot flood resolution. Before we dive into our presentation, we would like to thank our project liaisons, Jenna, Megan, and Megan King. And we will also like to express our gratitude to our project coordinator, Dr. G, and our project liaison, Dr. Lee. And my name is Ketia, and we're all part of the senior project design.
I'm James Lee.
I'm Thomas Griffith. I'm Michelle Goya.
And I'm Jerry Chen.
And for today's presentation, we're going over the background, the basis of design, the alternative design, the results, and then we're gonna explain our final recommendation and finish with our Q&A session.
So our project site is located south of Seattle near the Seattle-Tacoma International Airport. And as it's shaped like a baseball home plate, we'll also be referring to as the home plate site. The Des Moines Creek also runs adjacent to the site, and the Des Moines Creek is a habitat for fish like salmon and trout. It's also one of the few remaining urban salmon streams in King County, and this is where the runoff from our home plate site flows into. The home plate site itself was paved approximately 40 years ago and has about 500 parking spaces. It was originally intended for employee parking, but it's currently being used as parking for truck trailers. The home plate has a network of 7 catch basins and a bioswale with no filter media to the east of the site. For the catch basins, water enters from the grate and the inlet, and it exits through the outlet into either another catch basin or into the bioswale. For our current site, we currently have a major flooding problem on the southeast corner of the site, but there are also clogged catch basins due to the lack of maintenance, and the bioswale also floods during flood events. We also had to worry about the contaminants that are in the runoff that flow into Des Moines Creek, as it contains heavy metals such as copper and zinc from the brake pads from cars. Our main objective for this project is to remove the flooding in the parking lot and also to meet the water quality runoff requirements.
For each of our design solutions, we referred to the Stormwater Management Manual for Western Washington. Based on this manual, the pre-development conditions for the site, we used forested conditions with soil type C. Next, for the flow control on the site, we referred to 50% of the 2-year storm event all the way up to a storm that occurs once every 50 years. The flow control conditions for the pre-development conditions, or the current conditions, had to match or be lower than the pre-development conditions of the site. And for the water quality on the site, we needed 90 to 95% of contaminants removed, but the Port of Seattle requested 95% removal. So these are the 95% guideline is what we followed on our site. Next, we referred to the National Pollutant Discharge Elimination System permit for our priority pollutants on the site. As James mentioned previously, copper and zinc were 2 of our priority pollutants, as well as oil and grease, and turbidity and pH. Another pollutant that is not yet on the permits is 6-PPDQ. This is highly deadly to salmon and will likely be included on future permits. So we included this in our design considerations.
So for our modeling, we used the Western Washington hydrology model, which was a recommendation from Port of Seattle and the Western Washington Management Manual. We also used it because it's the standard continuous simulation model for Western Washington, and because it also complies with the stormwater management requirements. And lastly, we use it because it's a very efficient software to design alternatives to manage stormwater problems. On the right side, as you can see, it's a configuration of WWHM. We have a sub-basin which defines the area of the drainage elements. Then we have a catch basin which stores all the water and sends it to a bioswale through a pipe.
We used ArcGIS Pro to determine the contour lines for the elevations of the site, as shown in gray. And then we determined the flow direction, as shown in the blue arrow. Next, using the flow directions, we determined the delineation areas of the site. These delineation areas are the areas of water that flow into each catch basin. As you can see, we have the largest delineation area that flows into catch basin 1 down here. And here are the values we used in our modeling software. We also simulated the pipe flow directions, as shown in the green arrows. So the water flows from catch basin 1 up to 2, then to 3 and 4, and into the bioswale, which discharges into the creek. Here are the pipe elevations for the site. As you can see, the water flows from east to west and is collected in the different catch basins, and then it flows through the pipe into the bioswale. Here are the current conditions of the site. As you can see on the y-axis, we have the different storm events that we referred to in our model, and we have the blue line as the pre-development curve. For passing conditions, we need to have the conditions of the site match or be beneath this line. But as you can see, the current conditions fail the flow control results. We also had the water quality of the site was only 75% of contaminants treated, which did not pass the 95% guideline. Next, we searched for the source of flooding on our site. As you can see in the blue bar graph, we have the flooding for a 50-year storm event above each catch basin. We have the highest amount of flooding at catch basin 4, and in the model, we have simulated flooding around 1, 2, 3, and 4. The simulated water in a real-world situation would flow south to this depression area, but the simulation did help us determine the catch basin 1 was our main source of flooding as we disconnected it and saw a 46% flood reduction with significant flood reduction around catch basin 4. We also noticed, based on the flow contour lines, that we have a depression area here where all the water collects and does not outflow into a catch basin. So we need to consider catch basin 1 and this depression area in all of our design alternatives.
And to address the water quality concern on the site, we're planning on installing a new bioswale. However, as you can see, our site is surrounded by wetland area, and the green represent the wetland areas. And the stormwater management says that we cannot build anything on top of wetland areas, but as we can see, we have some available space on southwest of the site. And the purple rectangle represent where we're planning on installing the new bioswales. And this is a layout of bioswales. This is going to help us understand how bioswales work. Bioswales are a depression with shallow depth. They also have a riser to address the overflowing water. They are composed of several layers. The first layer is soil layer. The second one is the sand layer. And the last one is a gravel layer. And these layers have the filtering properties that allows the water to get filtered and remove all the pollutant, including 6 ppdq. And finally, the bioswales also have under-drain pipe at the bottom to collect the filtered water and send it to the nearest water body.
So moving on to our alternative designs, our team have developed 3 different alternatives addressing the flooding concerns at our site, with adjustments made revolving around catch basin 1, as it was found to be the cause of flooding. As Kessia mentioned in the previous slide, a new bioswale will be installed in the open grass area as one of our defaults for the 3 alternatives. On top of that, referring back to the issue of the depressed area shown in the blue polygon, a new catch basin 8 will be installed to capture water at this low point of the site, where the collected water will be directed to catch basin 1. For our 3 alternative designs, we have alternative 1, overflow bypass, 2, redirect flow, and 3, storage vault. For our first alternative, the overflow bypass, or in simpler terms, split flow, is designed with first splitting the outflow of catch basin 1 in 2 ways, where the main outflow will be directed to the new bioswale as shown in this picture. Once the water level reaches above the left pipe in the catch basin, water will also be directed to the existing bioswale on the other side of the site. For our second alternative, redirect flow, our first step would be to disconnect the pipe connecting catch basins 1 and 2 and redirect all the water from catch basin 1 to the new bioswale, and this means that we'll need a bigger bioswale size to hold all the water. And finally, for our third alternative, the storage vault design, our first step will also be to disconnect the pipe from catch basins 1 and 2 and install a vault in place of catch basin 1 with a vault size of 110 by 110 by 8 feet. Here's a video of how the storage vault will work. During a storm event, water collected from catch basin 1 will flow into the storage vault, and as time passes, settlements will be gathered at the bottom of the vault and clean water will be drained out slowly to the new bioswale. This will reduce the peak outflow in our drainage system. As a result, this design will have the smallest bioswale size out of the 3 alternatives. Here are the water quality results for our 3 alternatives. As you can see, all of them pass the 95% water quality requirement, with the storage vault having the highest percentage at 99.4% due to the sedimentation process that removes suspended contaminants from the water. As for the flow control results, our team have designed all these alternatives to pass the 50-year storm event, while at the same time limiting these results as close to the pre-developed conditions as we can. By doing this, we can prevent over-designing in our alternatives and save more money. Therefore, our 3 alternatives will have similar flow control results.
And here is our cost analysis result. The first row represent any construction cost related to the new structures that we're placing on the site. The second row represent the cost of the new bioswale. We wanted that to be separate from the first because the new bioswale represent a significant portion of the total cost. And the third row is the indirect cost. This include taxes, fees, and permitting. And lastly is the total row. As you can see, the storage vault is the most expensive option, while the overflow bypass is the least expensive option.
So in order to get our metrics, we first evaluated our value in terms of percentage. For cost, maintenance, and construction time, we use the following equation since the highest value should receive the lowest overall score. And we use this is the equation we use to get those value. And this is an example, sorry, of the cost of alternative one, which is the overpass flow. And then next, this is the table of all the percentage of all our alternative value. Next, we multiply all those percentage by the weight of scoring given to each criteria. As you may notice, the flood mitigation has the highest weight of scoring since flooding is our main concern. And next, we have the environmental impact since water quality is also the priority of the team. So by multiplying the percentage and the weight of scoring, we're able to get the score we have in our matrix. So for the first alternative, the cost has the highest score. For the second one, which is the flood mitigation, all the three alternatives have the same score. For the third one, which is environmental impact, which is related to the water quality of all three alternatives. Alternative 3, which is the storage vault, has the highest score. And then for the 10-year maintenance, alternative 1 has the highest score as well. And then lastly, for the construction time, alternative 1 has the highest score. In overall, alternative 1 has the highest score in our evaluation metrics and will be our final recommendation for the projects.
And as Mr. said, the overflow bypass is our final recommendation, and this is because it is also environmentally friendly, it is efficient at mitigating the flood, it is also the least expensive option, and it has the overall highest cost in the evaluation matrix. And here is a profile view of the elevation of the pipe, the new pipe that we're installing from catch basin 1 to the new bioswale. And this is now the end of our presentation. Thank you for listening to us, and we would like now to open the floor to questions.
We have time for a few questions. In the back. And for those who are online, can you repeat the question briefly?
Oh, yeah. So he just asked, how did we consider 6 PPDQ? So it was mentioned by the sponsors that it would likely be on future permits. And we did research into the treatment of 6 PPDQ, and we found that bioswales were able to treat 99% of 6 PPDQ in certain situations. So that's why we considered bioswales for each of our design alternatives. Does that answer your question?
Curious why you picked a 10-year time period and not a longer time frame.
This is because that's what our project liaison asked us to do. They wanted a 10-year projection, so this is why we did it. But, yeah.
I didn't really understand the value of the overflow. What's the value of having it?
You want to go back to that slide? Next. No?
So we found that doing the redirect flow and sending all the water from catch basin 1 into a new bioswale required a very large bioswale size. The overflow bypass divides the flow between the new bioswale and the old bioswale. So we had a smaller bioswale size, a smaller overall cost, and was able to meet our water quality and flow requirements as well.
All right, well, great. Thank you, team. So next up is team 24.3. So you can, welcome to come on down. Get ready, we'll queue up the presentation for you. Okay. Oh, wait, 1 minute.
Hi, hi everyone. We're Team CEE 24.3. I'm Laura.
I'm Julia. I'm Chelsea.
I'm Charlene.
And I'm Molly.
And today we will be presenting on the bridge replacement study of Cattle Pass Bridge 183, located in Snohomish County.
There you go. I think you have-
Okay. So today, we will start off with an introduction of our team and then some background information on the site. Then we'll get into our 3 alternatives, which were evaluated through an evaluation matrix, which helped us select our recommended alternative, which we took to 30% design. Then we'll close with a summary of our work, and there'll be time at the end for some questions. So this is our organization structure for this year. Starting at the top, we've been working with Tim Tipton as our liaison from Snohomish County. Professor Guven is our project advisor with additional support from Jeff Dye of Parametrics. And then Dr. G is our project coordinator. And the bottom row is our design team. Cattle Pass Bridge 183 is composed of multiple concrete girder unit, metal guardrail, and timber pile. The bridge is in poor condition structurally. Because of that, Snohomish County has requested us to come up with alternative ways for its replacement. The options will be evaluated into a decision matrix, which will provide us with a preferred alternative. All of this will be compiled into a type size location report, also known as TSNL report, which describes the project, the purpose structure, and the reason why the type size and location were selected. The bridge is located in Everett. It's about 30 miles north of Seattle, and it has a stretch of 6 miles. There is a stream adjacent to the project, but because there need to be additional analysis, it is outside of our scope of work. However, it is considered non-fish bearing according to the GIS Snohomish County. And so the first sign of structural damage was detected back in 1982, and upon recent inspection report, the bridge is categorized as sufficiency deficient, with a sufficiency rating of 35 out of 100. You can imagine having a score like that on an exam, you'll fail. And so from the inspection report, some of the deterioration include major rot in the timber pile, some collision damage in the guardrail, and vertical crack in the concrete. And now we're gonna talk about our 3 different alternatives.
So our first proposed alternative is an embankment. The design and construction were done in accordance to the WashDOT Geotechnical Design Manual. There will be a complete removal of the existing bridge conditions, and that will apply to all of the proposed alternatives that you'll be hearing about today. The underside will be filled with a combination of select borrow and soil material, which are the preferred materials used for embankment construction in this case. Layers will be laid from bottom to top and compacted to 95% maximum dry density in order to ensure there are no ruts or low places that could potentially hold water. For extra reinforcement, we will be using GeoGrid, which is a geosynthetic material that allows for extra tensile strength for soils. Lastly, the side slopes of the embankment will be 6-to-1, which may seem quite steep, but this is due to the fact that there are property owners on either side of the bridge and existing road, and we want to have a minimally invasive design.
For our second alternative, we designed a 3-sided concrete box culvert. One thing to note is that our site is not directly over running water. However, it is on the edge of the FEMA flood zone AE, which means that the site may experience the 100-year flood. After infiltration, however, we found that the base flood elevations would be below the ground elevation. So instead, we designed the culvert based on the criteria that a culvert spanning over 20 feet across the center line of a road is considered a bridge. And all this means is that the culvert would be subject to biannual inspections, which is typically what Snohomish County designs for. So with this in mind, we designed the culvert with a rise of 8 feet, a width of 21 feet, and a length of 43.6 feet. Our hope with these dimensions is that it would allow inspectors to access the culvert easily and do their job efficiently. Additionally, we propose to use shallow footing as the foundation that will extend through the length of the culvert. Initially, we considered using structural fill as the material above the culvert. However, this yielded in a 9.5 footing width. So instead, we proposed to use geofoam, which is an expanded polystyrene with a much lower unit weight. And this allows for a footing, it would reduce the load on the footing and yield a 4 feet wide footing width.
For our third alternative, we will have a replaced bridge, which will span the same length as our existing bridge, but will be widened to allow for a sidewalk, additional shoulder space for traffic, as well as the potential to add bike lanes in the future. The way in which we initially designed our bridge was using a software called PG Super, which is a bridge engineering design software for precast, pre-stress, concrete design, analysis, and load rating. The loading in which we used was an HL93 loading, and with that, we were able to find that 4 wide flange 42G girders were appropriate to hold a bridge of a span of 61 feet long and a width of 40 feet wide.
So to decide our recommended alternative, we developed an evaluation matrix with the top row being our 3 alternatives, as well as a no-build option. This allows us to evaluate the improvements of our design against the current conditions. In the left column, we have our 4 criteria with the corresponding weights for each criteria. And as you can see, the cost and environmental impacts will weigh more than maintenance and meeting project goals. We decided to rank the alternatives relative to each other, with 1 being the least preferred and 4 being the most preferred. One of the main reasons for this is most of our criteria is qualitative, and so we wanted to have a uniform way to evaluate each alternative. For our first criteria, we evaluated cost, and preliminary cost estimates were done based on the construction for each alternative. So that includes materials, labor, and equipment. As you can see, the bridge ranked the least preferred by being the most expensive, and the no-build option is ranked the most preferred because there are no construction costs. We use the WSDOT unit bid analysis tool to estimate the costs by looking at similar projects and then scaling each cost to based on the size of our project. Our second criteria, we evaluated environmental impacts. So for this, we considered the destruction of habitat. We know that there are birds nesting on the underside of the bridge, and while the adjacent stream is currently non-fish bearing, there is a potential for it to be in the future. So we want to maintain any wildlife passage or habitat that occurs there. For these reasons, we ranked the bridge as the most preferred and the embankment and culvert as the least preferred.
Maintenance refers to the corresponding care and upkeep of each of the alternatives. Additionally, it takes into account the regularity of inspections. Currently, since the existing bridge has a poor condition rating, it has required additional maintenance and extra inspections. Since our bridge will require biannual inspections, these inspections may identify potential maintenance needs. Also, as we mentioned earlier, the culvert is classified as a bridge, so it will also require biannual inspections. When compared to the other alternatives, the embankment was preferred because it required the least amount of maintenance. Meeting project goals refers to the fact that Snohomish County is in fact invested and interested in finding a replacement alternative. They are looking for something that is safe and also is tied into the corresponding changes in the existing area, as well as the growth of the area. Lastly, after each of the alternatives are scored in the appropriate criterion, those scores are totaled up and we end up with our final scores. The final score, the highest one, is the one that moves on to our recommended criteria, our recommended alternative. As the bridge is the highest as the bridge is the highest scored alternative, it moves on to 30% design.
So taking this design to 30% will include the further dimensioning of components within the sub and superstructure of our bridge. We have also undergone some geotechnical analysis to determine what kind of foundational supports we would require. We then furthered our research into the environmental impacts of our site to create a drainage plan and to also implement low-impact development methods. Lastly, we created a preliminary construction schedule to give an estimate of what the progression of building this bridge would look like. So here we have an idealized model of our bridge, and as previously mentioned, we will be using 4 wide flange 42G girders. Above this, we will have the bridge deck along with 2 approach slabs at each end extending 10 feet past the bridge length. These will then sit on an abutment wall, which is at a height of about 16 feet, meeting the bottom of the girders and the existing ground. It will then be connected through a semi-integral connection, which allows for movement within the girders and also eliminates the use of expansion joints. The wing wall will then extend perpendicularly, matching the extension of the bridge of the approach slabs above. The structure will then sit on top of the shaft caps, which will act as the footing for the drilled shafts within the ground.
In order to determine the diameter of the drilled shafts we use, we've had to take into account the loadings and weights applied to our bridge. We did this by analyzing each individual girder, and shown here is a sample calculation of girder A. First, we found all the components of the reactions, and we plugged all of these into a load combination factor equation, and the components include the weight of the concrete, the wear and utilities, truck loadings, and as well as lane loadings. With this, we are able to find that girder A had a total loading of around 214 kips. Doing these again for the rest of the girders, we found that the total loadings on all of the girders were around 850 kips. In addition to this, we also had to take into account the dead loads of the abutment walls, which we found to be around 200 kips. And adding all of this together, we found the total loading of our bridge to be around 1,050 kips.
So once we determined the load demand of our bridge, we then needed to assess the soil conditions of our site. Using the provided geotech report, it was determined that at a depth of about 17.5 to 26 feet, we would be reaching a material of glacial till. We want our drilled shafts to sit within this material because it is known for its structurally stable and foundation-bearing properties. We then decided to split the load between the 2 abutment walls and to have 2 drilled shafts underneath each. This will create a load demand of about 120 tons, and meeting this depth, we see that they intersect on the 2-foot diameter shaft plot. With this, we end up with a final drilled shaft dimension of 21 feet in length and 2 feet in diameter.
For our roadway design, we will be widening our road from the existing 23 feet to 40 feet wide. The figure on the top shows an existing cross-section view of our bridge looking in the northwest direction. As you can see, there are 2 11-foot travel lanes, and on either side, there is a half-foot shoulder. The figure on the bottom shows the proposed cross-section of our bridge, which consists of the same 2 11-foot travel lanes, but on the left-hand side, we will be adding a 6-foot sidewalk as well as a 4-foot shoulder. On the right-hand side, we will be also adding a 6-foot shoulder, and on both sides, we will be adding 1 foot for railings. In addition to this, the way that we will be tapering back from the 40 feet of our bridge back to the existing 23 feet of the rest of the road is by doing at the end of our approach slabs.
There is no drainage facility currently, so in order to fulfill the minimum requirement of Snohomish County Drainage Manual, we propose to install a bioretention swale that will remove pollutants and decrease runoff. So we followed a requirement from the volume 5 of the Drainage Manual, and we model the simulation into the Western Washington Hydrology Manual to make sure, to make sure that the swell will filter 100% of the runoff. In our design, we have 4 catch basins, one on each corner of the bridge that will pipe through the swell. And also the drainage manual is very adaptable to various settings. So we base our design criteria on the fact that the swell will filter 100% of the runoffs. So with that, we came up with an area of 12 by 3 feet and a total depth of 5 feet. And we also propose to install the swell on the northeast corner of the bridge, represented by the red rectangle. We are coming to the end of our presentation. So we propose 3 alternatives with a no-build option included. We selected the bridge as our preferred alternative, and we took it into a 30% design. Thank you so much for listening to our presentation, and now we are opening the floor for questions.
Any questions?
So for your bioswale, are you just capturing the water or are you also taking water from
Yeah, so the catch basins will be on the outside of the approach slab, so it will really be just the bridge deck and then the 10 feet from the ends. Yes, there is on one side a pump station that currently exists, and then on the other side there is some other structures, and so we're really trying kind of to evaluate where's the best place and where there's enough space to put it. Yeah, so also it is within our right of way, so in that location, we don't need to purchase any more land, so it's also more economical. Yes, in our report, we propose 2 alternatives for construction, how the traffic will be directed, and the recommended is to reroute traffic, because installing a new bridge, a temporary bridge will be more cost. And so it's about, I think, a 30-mile rerouting, so it's the best option.
If not, thank you, team. Okay, and our final team for this session is team CE 24.2. Welcome to come on up. Not working. Do you have the other one? I think it might be. I think it might be just that it takes a while for it to. This is the one that we're, see the mouse is moving.
Probably gonna switch.
Okay. I think we're ready. All right, it's all yours.
All right. Hello, everyone. We are CEE 24.2. My name is Mark.
My name is Jed.
My name is Ifra.
I'm Ella.
My name is Emmanuel.
My name is Edward.
And today we'll be presenting our senior capstone project, the Diablo Powerhouse Bridge Inspection Platform. For this presentation, we'll be going over the project management structure, background, constraints, supporting elements, our design, and finally, we'll answer any questions at the end. For the project management structure, we've been working closely with our liaison engineers, Robert Cochran and Doug Smith from Seattle City Light, as well as our faculty advisor, Dr. Smith, and design coordinator, Dr. G. And the 6 of us make up CE 24.2.
So first we'll go over some background on our site location. The Diablo Powerhouse and Dam is located approximately 125 miles northeast of Seattle. It's a part of the Skagit Hydroelectric Project, along with the Ross and Gorge Dam, and makes up about 20% of Seattle's power. The Tailrace Bridge itself, as seen in the image right here, is sandwiched between the substation and the powerhouse. This bridge was originally built in the 1920s as a railroad bridge, but in the 50s, the rails were removed and replaced with a metal decking, and it is now used to transport heavy machinery to remote site locations. For our project, we were tasked with creating a suspended working platform to be implemented underneath the Diablo Tailrace Bridge so inspections can be done with ease. Currently, in order for them to do those inspections, they have to shut off the powerhouse as the water outflow is directly underneath the bridge, which costs about $100,000 per day. And then, as pictured in the image here, use a boat or barge to gain access to the underside. So by providing this platform, we are creating easy all-year-round access to the underside of the bridge and saving money by not having to shut off the powerhouse anytime an inspection or repair needs to take place. So these are a few constraints that we had to consider while making our design. First, underside bridge visibility. We had to make sure our platform was high enough to be able to have hands-on access to the top of the grading, but also low enough so that we can have hands-on access to the bottom of the 6-foot girders. Similarly, with water level, we have to make sure that our platform was high enough to where the platform will not be completely submerged the entire time, and low enough so that the workers have ample room to do what they need to do. There will also be a 1 in 10,000 and 1 in 100,000 water event where the platform will be completely submerged, so we have to use materials that are corrosive resistant. Next, constructability. We want to make sure our platform is mostly pre-constructed off-site so that the implementation process is quick. Next, load capacity. We want to make sure that the demand of our platform does not exceed the capacity of the existing structures. And finally, safety and environmental. We want to implement things such as handrails and kick guards so that things and people do not fall into the water below.
In this figure shown here are just the main components for this project, that being the supporting reinforced concrete beams, the existing Tailrace bridge, and finally our proposed inspection platform. In this image shown here, highlighted in yellow, are the 2 reinforced concrete beams. We did an analysis of these beams' capacity and demands so that we could make sure that the platform can anchor safely to those beams and remain reliable. In order to do the analysis, we had to consider different types of loads. This first image is showcasing the type of snow you could expect to accumulate up in Diablo. And the next image is the Tailrace Bridge once again, on the left and right side being the switchyard and powerhouse, where you could find heavy machinery and equipment, as well as people who will travel through this bridge. Knowing the types of loads these beams could anticipate, we came up with a controlling load combination that takes into consideration the live loads, dead loads, and snow loads. So now I'm going to pass on to Manuel to go into the analysis.
So due to the uniform load as well as our platform, we can anticipate that the reinforced concrete beam will have some deformity. So shown here is a very exaggerated model example as to the type of deformities that we can anticipate. So we see that the deformities typically occur at the center and at the ends of the beam. And highlighted in green are the areas in which the beam will experience the most amount of tension. And something to note about concrete is that concrete is very weak in tension. So these areas are subject to cracking, which is why this is where we selected these regions to analyze for the demand and the capacity. So shown here, we see that for the shear, we have the ends where the most amount of demand is felt. So for the shear, we obtained a demand of 200 kip. And for the bending moment, we see that the most amount of bending will occur at the midspan and at the ends. And we obtained a demand at the end of 1,072 kip feet. And at the midspan, a demand of 1,260 kip feet. So in order to conclude that we can actually, that the reinforced concrete can actually support our platform, we conducted a demand to capacity ratio, demand being the load that's being applied onto the reinforced concrete, and the capacity as to how much the reinforced concrete can actually hold. So for the shear, we obtained a DCR of 0.45, and for the moment, both at the end and at the midspan, we obtained the same DCR of 0.26, and the goal is to remain under 1 being total failure. So as we can see, all 3 DCRs are under 1. Therefore, we can conclude that the reinforced concrete can support our platform. Next, I'll pass it on to Efra to speak about our platform characteristics.
And before we get into the design of our platform, let's take a look at some of the characteristics highlighted in red. Our platform will consist of 2 spans, each being 50 feet, and they will be placed in between either side of the abutments, as well as the interior pier. And on either side of the abutments will be manhole stairs that will provide access for the inspectors so they can get from on top of the concrete roadway all the way down to our proposed platform. And shown here is a 3D model of our proposed platform as well as the existing bridge. In dark gray are the existing reinforced concrete beams. In light gray is the existing bridge. And in green is our grading that we chose. The blue are the beams, the red are the girders, and the purple are the HSS posts that will act as handrails as well as be anchored into the reinforced concrete beams. And for our manhole hatches, they will be located on either side of the existing bridge on top of the concrete roadway. And for our manhole hatch, it will have a length of 16 feet, a width of 5 feet, and a depth of 8 feet. And as you can see and highlighted in yellow hatching is the steel grating that will be placed on top of the manhole so that trucks will still be able to drive over it without having to fall in. And shown here is a ladder. And shown here is a ladder that the inspectors will be able to use to get over the concrete column that exists that prevents clear stairway access straight all the way down to the proposed platform. Next, I'll pass it on to Emmanuel to discuss the cross-section view.
Okay, so here we have a cross-sectional view as to what our platform will look like being suspended from the 2 beams. So we can see that our platform will have a clear space of 3 feet. So that will allow our inspectors to go underneath the girders. Our bridge will have a capacity to hold a crew of 4 per platform, as well as our platform was constructed with a 200 PSF live load. And to give some context as to how strong that is, typically the concrete that is poured for a 2-car garage is typically around 40 PSF. So our platform is actually 5 times stronger than what a typical concrete slab for 2-car garage is. Next, I'll pass it on to Jed to speak about the building materials.
So our platform is going to be composed of 2 primary building materials. The first of which we see here, fiberglass. We chose fiberglass for its non-thermal and non-electrical conducive properties. It is also slip and rust resistant, and it has an excellent strength to weight ratio. Our next building material is going to be galvanized steel. Galvanized steel is produced through a process called hot dipping, wherein the desired steel member is dipped into melted zinc, and from this we get our galvanized steel. So galvanized steel is also rust resistant, and if we make our platform out of this material, it's going to give the platform an extended lifespan of more than 50 years. So as you can see here, we're looking at a longitudinal elevation of our platform. To the lower left of our screen, we are looking at our 3D model that was introduced earlier. So this is to help orient us as to where we're looking at. And as you can see, our platform, this is one of our platforms, is composed of 3 spans of 16 feet. Continuing on with our dimensions for our platform, as you can see, our platform's beams are spaced at 4 and 3 feet. The platform itself is going to be 14 feet wide, and there's going to be a clearance between the top of our platform and the bottom of our existing girders of 3 feet. So continue on with our platform. Highlighted in green is our fiberglass grating, atop which our users are going to walk on. To the sides of these are our kick guard plates. This is meant to prevent materials that may be dropped by the users from rolling off of our platform. These sit atop of our W10 by 19 beams highlighted in blue, which in turn sit on top of our red W10 by 26 girders. We're going to install handrails for our platform to prevent users from falling off. And our system, this platform is going to be suspended by HSS posts. These posts are going to be welded to our plates, highlighted in orange, and it will be in turn bolted to our existing concrete beams with epoxy bolts.
Now here we're looking at the concrete anchoring of our platforms. As we can see, there are totals of 8 bolts, anchoring bolts that we're gonna install to the concrete beams. And we also have a plate, which is located 12 inches from the bottom of the concrete beams. The reasons we are doing 12 inches is because it's to prevent the concrete anchoring from interfering with the existing concrete reinforcements. And here we are looking at the concrete anchorings from the cross-sectional view. We have embedment bolts of 6 inches and a spacing also 6 inches. The reasons we are using epoxy bolts is to prevent water from entering the space within the holes. So it prevents corrosions of the bolts itself. And here we are looking at the girder to hollow structural sections, mainly the purple and the red members. So we're gonna make a cut into the HSS member, and a plate is going to be inserted into the HSS and be welded at both ends with a weld thickness and a weld thickness of 1/4 and length of 6 inches. And this plate is also going to be bolted into the web of the girder with a bolt diameter of 7/8. And here we are focusing on the beam girder connections, mainly the blue and the red members. In between these members, we are gonna install a plate in between these, and it's going to be bolted into the flange of the girder, and it's going to be welded into the bottom flange of the blue member. Moving on, I'm gonna pass it to Ifra to talk about the cost estimate.
Shown here is a material cost estimate of our platform. And as you can see at the very left column are each of the line items of our platform. After some discussion with Seattle City Light, we were able to find a unit cost of about $3 a pound. And from there, we were able to calculate each of the weights of our line items, multiply it by the unit cost of $3 a pound, and find the total cost of our platform of about $171,000.
So in summary, by providing this platform, we are creating easy all-year-round access to the underside of the Diablo Tailrace Bridge, and in the long run, saving them money by not having to shut off the powerhouse anytime an inspection needs to take place. Thank you so much for listening to our presentation. We will now be opening the floor for questions.
Can you repeat the question?
The question was, why did we choose to have stairs instead of a ladder that goes straight down? After some discussion with Seattle City Light, we were and as well as getting some feedback after presenting to some of the members from Seattle City Light. They proposed that having a staircase would be the safer option than having a ladder straight down, because we want to have a hatch that's also big enough to where, and if an accident was to happen, that another person was able to safely pick someone up and just go up the stairs rather than just pulling them up from the ladder.
And then as far as the actual coverage of that, did you evaluate that?
Yes, we are planning on bolting it in so they could just open it easily, but that wasn't something, yeah.
So the anticipated flow rate, unfortunately, we did not do any water flow analysis, so we do not have that answer.
The question was, if I'm remembering correctly, why we use galvanized steel rather than stainless steel for environmental impacts?
Yeah, typically.
Yeah, well, just our main reason for using the galvanized was just so that it wouldn't be affected by the water and corrosion resistant. We didn't think that stainless steel would provide that same security with our bridge.
So the main things that will be done offsite will mainly be the stairwell, which we anticipate to be precast concrete, precast stairwell, sorry, as well as all the welding we want to do offsite. So get all that done and then just get that dipped into the zinc to galvanize it first, just simply because when it's galvanized, you can't really when you weld it, it doesn't really stick well, the two materials. So we want to anticipate to make sure that that's done offsite. And then for the onsite, we plan to remove the grading and have a team go in and pre-drill the holes for the concrete, for the anchoring. And then at a later date, again, remove the grading, the deck grading on the bridge, and then come with the crane, bring down the HSS post with the welded plate, and then start anchoring them. And then close that up, come underneath with the barge, and then start lifting up the girders and the beams, start those connections on site.
Okay, well, thank you, team. So that concludes the civil and environmental engineering program presentations, but there are a lot of other interesting presentations today. So I encourage everybody to come back in 15 minutes for environmental science and Masters of Science and Data Science presentations. Many of them relate to similar issues. And for the civil engineers, we'd love to get a group photo. So I'd ask you to stick around for just a few minutes. We'll get a group photo with everybody together, and then you can head out to your posters. There are posters outside, so I encourage everybody to view the posters for the teams too. So join me again, thanking the students. Thanks. So welcome. I know there's always a little bit of resorting for these presentations, so I'd like to introduce the order of events right now. So first of all, these are the culmination of a lot of work that happens over the course of a year, or in the case of Masters of Science in Data Science, 2 quarters, right? So, but they're always team-based projects that involve a faculty sponsor and an outside sponsor. It's a lot of, there's a lot of work that's contributed on all sides. So it's always worth thanking everybody for their work. So join me in thanking all of those who have brought these projects together. So we're going to start with a team of environmental scientists. So environmental science team 24.1. And then the second and third presentations will be the MSDS presentations, and Ariana Mendible will be introducing those teams. So with that, I'd like to invite team 24.1 up.
I'm Shannon.
My name is Joe.
I'm Sarah.
I'm Luke.
And I'm Patricia. And we are Team ENSC 24.1, and we're here to talk about evaluating the General Levee Setback project. So our personnel structure this year has involved 3 liaisons from King County, including Jess Hardy, Alex Lincoln, and Mark Rubel. Dr. G has acted as our project coordinator, and Drs. Riazi and Dr. Lauer have acted as our faculty advisors. We'd like to personally thank King County and the Flood Control District for allowing us to work with them throughout the year, as well as our advisors and project coordinator and everybody at SU who's allowed this project to happen. So a quick overview of our presentation. We're going to start with the background of the project, including the project site location and the original project design for King County's General Levee Setback. We'll then dive into answering our 4 main research questions supported by the results of our data and collection and analysis. And then we will do a quick recap of our conclusions. So the project site seen here is south of Seattle along the Cedar River near Maple Valley. It is proximate to the Cedar River Trail 7 revetment, as well as other public infrastructure, including a road which provides the sole access to the surrounding community. The King County's task at this site was to remove the old levee seen in red and replace it with an extensive levee setback seen in yellow. To divert flows, they constructed that constructed side channel that you can see, and they also implemented multiple large wood structures seen as yellow dots in both the main and side channel. Their intention with creating these changes was to reduce the flood risk to the surrounding community and infrastructure, as well as increase the suitable habitat for rearing Chinook salmon. Our task at the site was to conduct field monitoring of the site to evaluate its current hydraulic conditions, and then to take our data and compare it to a 2D HEC-RAS model, which is a hydraulic model that King County is using to efficiently map and evaluate the entire site reach, both post and pre-levee. We were also asked to determine the best monitoring methods for similar projects based off of our experience at the site. Our 4 main research questions are: what are the limits of the hydraulic model? How has salmon habitat changed post-levee setback? How has flood risk changed post-levee setback? And what field monitoring methods do we recommend?
All right, taking a look at our first research question, we looked into the limitations of the hydraulic model that King County used to evaluate the site. And how we did this was through data collection. Our first methodology was using the ADCP, or the Acoustic Doppler Current Profiler. This is a device that we dragged throughout the main stem as well as the side channel to create a transect of depths and velocities that we could compare to the model's output. In a similar fashion, we also used the velocity meter in the side channel, specifically at those 25 points that you can see on the left side of the screen, to also get velocities and depths by which we could compare to the model. And our overall finding is that the hydraulic model overpredicts the amount of flow into the side channel. And we know this based on our constructed rating curves as well as the percent discharge comparison.
As for the rating curve, so a rating curve is going to be a graph of the water surface elevation at a particular point within the channel versus the discharge of that channel. So taking our ADCP collected data shown in the colored triangles along with the labels, we plotted that on the same graph with the modeled values, which are going to be seen as the blue triangles. So if our collected data fits the modeled trend, that's a good indication that that the model is accurately representing what's happening in the channel. So if you take a look here, the R-squared value is fairly high, which is a good indication here that our data is fitting the model. And especially with the small relative error, this is also a good indication. And when we zoom in to look at a truncated version of this, you can see that our data points are fitting along that model, indicating that in the main stem, the model is doing an accurate job at depicting observed flows. We did the same thing in the side channel, and as you can see here from this graph, there seems to be a little bit more variation compared to that of the main stem, especially with the higher relative error between them at 0.12, and we can zoom in and see that our data does not fit what's happening at the model from the side channel, meaning that the model is not accurately depicting what's happening within the side channel.
Taking a deeper dive into the side channel comparison, we used a C parameter, which is a modified version of Manning's equation, to assess the depths and velocities from our collected data as well as the model data. We plugged these depths and velocities in, and this allowed us to see the differences between the hydraulic gradient or the stream slope, as well as Manning's roughness coefficient. And as you can see on the right, the modeled C parameter is higher than our collected value, indicating that for the modeled values, the stream slope or hydraulic gradient was either overestimated or the Manning's roughness coefficient was underestimated. Separately, the average percent discharge that was diverted into the side channel from the main Cedar River is a lot higher than our collected data, which supports the same conclusion. In this picture, you can see the mouth of the side channel and the engineered log jams. This picture was taken right after project completion in 2022. And this picture shows the same location this April. As you can see, there is a debris dam that has formed that is likely the cause of this overestimation in the model. This is because in the model, it did not take into account the volume of all of the debris that piled up there.
The next question to answer is how has salmon habitat changed post-setback? We've concluded that there is an overall increase in suitable habitat for Chinook salmon, evidenced by an overall higher coverage of high habitat suitability index values, especially along the side channel, and an overall more diverse habitat for salmon. So really quickly, what is a habitat suitability index, or an HSI? An HSI is a numerical evaluation of the hydraulic suitability for a given species based off of that species' preferences for depth and velocity. The Washington Department of Fish and Wildlife has created these suitability curves for rearing Chinook salmon, which we've used throughout the project. And essentially, any measured depth or velocity value will correlate with a preference score. These preference scores will then be multiplied together to give you one singular HSI value, which ranges between 1 and 0, 1 being considered the ideal habitat for that species.
We used velocity and depth values to calculate HSI values for the entire project site. This change map of the main stem shows an overall increase in HSI, specifically in the upstream end. If we zoom in closer on the constructed side channel, it's mainly characterized by areas of moderate and high suitability. One of King County's goals for creating the side channel was creating beneficial habitat for juvenile Chinook salmon, and this model data shows exactly that this goal is being met. One way that we can assess whether or not habitat is being evaluated properly and whether or not it is actually good is by counting the number of fish that are in that habitat. These two maps are the summary of snorkel surveys performed pre and post levee setback by King County. They're noted by the yellow polygons seen in each of these maps. The main finding of these was that there was a positive shift from low and moderate fish being in low and moderate HSI areas in the pre-project condition to more fish in the high suitable areas post-project condition. However, there are a few considerations that the model does not take into account when we evaluate HSI solely based on depth and velocity. These considerations include things like food availability, the presence of predators, as well as water quality, but also take into account indirect things such as the seasonality of juvenile Chinook salmon. It's important to note that not the same amount of juvenile Chinook salmon will return to the Cedar River every year.
Another metric we used to gauge habitat quality was through pool, riffle, and run delineations. Pools, riffles, and runs are habitat types found in rivers, and they're significant because having a diverse distribution of these habitat types helps support salmon across life stages. We used two delineation methods. First was numerically using the depth and velocity outputs of the model inputted into the Froude number equation to produce a range of values that correspond with pools, riffles, and runs. And you can see that pools generally have a lower Froude number and riffles have a higher Froude number. The second method was visually, and this was done manually in the field with observations that we see. And this is where we take into consideration the speed, depth, width, and location of these habitat types to produce maps like this. On the left, it's the modeled result with the Froude number, and on the right is the manual delineations. It's important to note the missing data in the manual delineations. This is because manual delineations are very subjective in nature, and we can only record areas where 3 or more group members agreed. This leaves areas of disagreement which have to be left blank. We also performed delineations from drone footage after the fact. Again, on the left is the modeled, and on the right is with drone footage. There's less missing data here, but it's important to consider that missing data might be a factor of manual delineations. We also had to compare pre and post levee setback conditions. Since a delineation was not done manually pre-setback, we have to rely on the model for this. On the left is pre, and on the right is post. You can see that not only was habitat diversity increased with the addition of the side channel, it also increased in the main stem as well. Again, this is significant as salmon benefit from diverse habitat types.
A third question that King County asked us to evaluate was how flood risk changed post-levee setback. To do so, the team looked at water velocities, as King County had a goal to reduce flows in areas of concern. The team found that the model reflects decreased velocities in these areas of concern during flood events. This was mainly looked at in order to avoid disasters pictured here, where in 2009, a flooding event occurred in the project site that exceeded the 100-year flood. We did a change. Here's a change map of our pre and post levee setback velocity modeling for the 100-year flood. Areas of concern include the CRT7 revetment, highlighted in yellow, located at the bottom of the project site, and in the residences off the project site at the top of the map. The blue colors in these areas indicate that the model does see a decrease in flood risk, and could also refer to a less inundation of water, specifically in the residential area.
Our final question was, what sort of field monitoring methods do we recommend? Our goal here in taking a look at the ADCP, the velocity meter, and the drone is to help King County inform their decisions of what kind of methodologies they would like to use depending on what sort of monitoring techniques they would like to perform. So in summary, with the ADCP, we recommend this the most. This is mostly due to its high levels of robustness, which we defined as the ability to do multiple different types of analyses based off of one transect. So you can do hundreds of different analyses based on all of the different types of outputs it can give you. Also due to its high scalability, which is because it can be used in many different types of channels. As for the velocity meter, we recommend this the least. This is because of its low scalability and robustness stats, as you can only get one depth and velocity measurement within weightable channels. Lastly, the drone is a place where King County can look more into exploring this. There's a lot of different emerging technologies, such as particle image velocimetry, which allows for you to obtain velocity measurements simply by flying the drone and recording the river overhead. So maybe having a drone flight can give you an understanding of what's going on and what the project site looks like, as well as getting you velocities. So this could be an avenue for King County to go for in the future. In conclusion, we want to ask the question is the project on track to meet project goals? We ask this because it's only 2 years post-project and there's still a lot of time ahead of this project to see if it meets King County's goals. With that being said, we think it is on track. Simply put, we've noted an increase in salmonid habitat suitability as well as a decrease in overall flood risk. With this being said, changes must be monitored, namely the debris dam in front of the side channel. It must be monitored what changes to flood risk or habitat suitability this change might have. We also wanted to ask the question, is the hydraulic model a good aid in monitoring project outcomes? We think it characterizes the main stem well. You can see from this rating curve with this nice R-squared value. It also allows HSI values to be modeled site-wide as well as pool, riffle, and run delineations to be done efficiently to create nice results like this that might not be possible with other methods. It also allows for direct pre and post project comparisons like this, which again is very useful in seeing if a project is having its intended impacts or not. With all these things taken into consideration, we think the model is worth the cost and effort associated with producing it and should possibly be used for other projects in the future. I would now like to open the floor to any questions from the audience.
Yeah, so the Manning's roughness coefficient was actually manually input into the model by King County. So one of our solutions that we outline in the report is changing this Manning's roughness coefficient, especially at the mouth of the side channel, to account for the flow that we actually see. It's just a way to model the friction of the flow that might, how did they get the Manning's rough? I'm actually not sure of that, to be honest. I just know that it is an input of the model and that one of our recommendations is to change that in the future for similar projects.
What's more reliable to look at the one? Is it more accurate to rely on the model or based on? Can you repeat the question for anyone who's online?
Oh, yeah. So what is more reliable for habitat delineations, whether that's the model, whether that's drone delineations or in-person delineations? And it sort of really depends. There's drawbacks and benefits to each one. As for the model, you can do it site-wide very quickly. And there's a lot of literature out there that does define what fruit number would be best for which types. But as for the field delineations, models aren't always accurate. And so maybe being able to be there in the field is going to be really good to get something that is more accurate. And same with the drone as well. There's a drawback with the drone. You can't really tell depth very well. So there's a pro and con with everything, but it really comes down to what do you have the time to do and is that model accurate enough?
I think just monitoring the entrance to the side channel, as Sarah noted, is going to be the major thing. I think they can rely on the model for anything they want to learn about the main stem, but seeing if it's been predicted that during like annual flooding events, the debris along the side channel will be removed so that there will be a bit higher flow after those events. And just to track and see if that does indeed happen or if more continues to build up will be a really important part to ensure that the side channel doesn't dry out or something like that.
Thank you, team.
Okay, so now we'll be transitioning into the Masters of Science and Data Science presentations. We have two talks that both have to do with public utilities, so it fits well into this session. I'm really excited to have our students present the hard work that they've done. So first, we're going to have the Chelan County PUD team come up. Let's welcome them with a round of applause.
Hello, everyone. Thank you for coming here today. My name is Jeffrey. I'm here with my team, Ava, Lakitha, and K-Wall, and we are MSDS 24.2. We're here to talk about our project, which is modeling complex hydrodynamics in Washington reservoirs, sponsored by the Chelan County Public Utility District, or PUD for short. So, who is Chelan County PUD? Chelan County PUD is a nonprofit customer-owned utility company based in Wenatchee, Washington. They run electric, water, wastewater, and telecommunication services and serve about 50,000 electric retail customers. They currently operate 3 hydroelectric dams, 2 of which are situated on the Columbia River, which are the Rocky Reach and Rock Island dams, and 1 that is situated on Lake Chelan. So currently, Chelan County PUD faces challenges with managing the dam's control programs. Their protocols include the storage and release of water going in and out of these dams. It's very essential for Chelan County PUD to understand the flow rates of water going in and out of these dams so they could efficiently generate hydroelectric energy, but at the same time be mindful to not overfill or underfill these dams. As you can see from the map, for emphasis we're doing Rocky Reach and Rock Island. Rocky Reach is highly influenced by the Wells discharge and the Chelan NTF flows, while Rock Island is highly influenced by the Rocky Reach and Wenatchee inflows. So our methodology includes making documented Python code that represents 2 models for both the Rocky Reach and Rock Island dams for various flow conditions and for various flow conditions and hydraulic conditions as well. We accomplished this by using collected 1-minute interval data from 2019 to 2023 for various flow variables from both the Rocky Reach and Rock Island dams. And at the same time, we also look to forecast efficiency of dam operations and explore the relationships between headwater elevation and discharge to other external factors such as weather and pricing. So to move forward with this, we're going to be talking about our first model.
Thanks, Jeffrey. We are talking about improving models. Let's start by explaining our model. Consider this simple mathematical model where we input various features to predict an output. So in our project, these features are various water flows, and using them, we are predicting headwater levels at the dams. But how do you know our model is performing well? For that, we are using a statistic called R-square, which tells how much variation in headwaters our model can explain. An R-square of 1 means our model accurately predicts the headwater levels, indicating 100% of variance. Whereas R-square of 0 means the model predicts no better than random guesses. So we want our R-square to be as close to 1 as possible, indicating nearly 100% of variance. Traditionally, Rocky Reach inflow is calculated by adding the averages of its upstreams. For example, Wells Dam discharge takes 90 to 105 minutes to reach Rocky Reach. So averaging in that time period and adding it with other upstream sources gives the inflow. Then fill rate is calculated by subtracting the discharge from this inflow. And modeling this fill rate explains only 1.1% of variance in our headwaters. And a similar approach is used for Rock Island to calculate the fill rate, and modeling in a linear model explains only 19% of variance. To improve this, we incorporated more detailed data. So instead of adding the averages, we added all the 1-minute data into our modeling. So we have all the upstreams 1-minute data from date time frames and previous 2 minutes headwaters and discharges of Rocky Reach. So this gave around 52 features, but isn't it complex to model with 52 features? So we used a feature extraction method called PCA. PCA doesn't remove these features, it transforms these features into principal components in the direction where there is maximum variance. So you can see in the picture, like feature 1 and feature 2 are transformed to principal components in the direction where there is maximum variance. So PCA reduces the dimensionality while preserving more significant variances, filtering out noise and redundant information. Thus, it gives principal components that shows essential data variations. Then, using cross-validation, we found that only 16 principal components are enough to represent all these 52 features, and modeling used those features gave 99.4% variance in our headwaters. You can compare the traditional and PCA model over here. Traditionally, the headwater levels are kind of constant, but we can see the PCA model fits the data more perfectly. But how many of you are thinking our model is overfitting from this plot? We had that doubt, and we separated 2023's data and evaluated on that data. Even that explained 99.5% variance in our headwaters. A similar approach is used for Rock Island, and even that gave 51 features. And to reduce the complexity, using PCA, we found 22 optimal components, and evaluating on 2023's data provided 99.6% variance in headwaters. So our model says that Rocky Reach mostly depends on its previous values and Welch Dam compared to Chelan and NTR flows. And Rock Island mostly depends on its previous values and Rocky Reach compared to the Wenatchee flow. And one of the main concern is seasonal patterns in our data. So Keval will explain the seasonality.
Thank you. So as Likita elaborated, we have employed PCA to refine our model, providing a robust foundation for our predictions. Now I'll take you through the seasonality of this model. So what is seasonality? Seasonality introduces a cyclical change in the model behavior, dance behavior, due to the factors like precipitation, temperature, different kind of water uses for different seasons, creating a distinct data patterns. So all the seasonal dependencies can significantly influence the model's predictive performance, as it affects the key features that the model uses to make predictions. That's why it's really important to understand these patterns to enhance our model's accuracy and reliability. So on this slide, we are presenting a comparison of our model's performance for 2 different days. That is January 1st, a day in winter, and July 15th, a day in summer. So all those blue and green data dots are representing data points, which is plotted in between a predicted value versus the actual value of the headwater elevation. And the dotted line in between shows the perfect prediction line. So if a model were perfect, all those dots would lie perfectly on that line. We can see that for winter, our model explains about 92.7% of variance in the data, which is quite impressive. But when it comes to summer, the model outdoes itself by explaining almost 99% of the variance in the data. So this difference in the variance is clearly indicating that the importance of taking seasonality in our analysis. So we saw that our model somehow fits the summer data better than the winter data. That could be because of the increased variability in the weather pattern, which we might need to consider in our analysis. And we have considered all of those scenarios in our analysis. So moving forward, we are shifting and expanding our horizon from daily to quarterly, as it allows us to capture broader trend and consistent patterns. In our previous daily analysis, we saw that the difference in the analysis does exist and it's real, but it's a quarter-long analysis that will give us a clearer picture of how the seasons are influencing the model and the dams overall. So it's important because it's about reliability, and it also enables the informed decision making. So with this information, the PUD can decide how to efficiently operate the water discharge for different needs for the different seasons. So how we approach this? So we have segmented the year into 4 distinct quarters, and then we are evaluating all the quarters and its analysis based on the key metrics like R square. And we saw that the principal components and the most influential lag variables are quite different for different quarters. This difference clearly shows how the seasonality is impacting our model predictions. Also, these quarter-long studies, now we better understand and adapt to the cyclical pattern in the dam behavior, making our forecast more reliable and hence accurate. So for the rest of the analysis, Eva will take over.
Thank you. Hopefully this mic is working. I can't tell.
Sorry about that. For the next part of our analysis, we looked at time series modeling. Time series helps us by taking past values and forecasting future values. And we wanted to do this to forecast headwater elevation levels. We did a variety of models, including autoregressive, moving average, and ARMA, which is a combination of both AR and MA components. And we took our headwater elevation data and averaged it monthly in order for us to predict 2023 data. So from statistical measures, we compared a variety of our time series models, and we found that AR1 was our best fitting model. And as you can see from this plot, when plotting the actual 2023 data that we had of headwater elevations and the forecasting, it did not accurately predict the headwater elevation correct. So while forecasting performed worse than our PCA and linear models, this helps us understand our data better, that there's a lot of seasonality within this data, which makes it hard for predicting and forecasting with time series. So for the next part of our analysis, we will look at external factors, weather and pricing. For weather, we took hourly weather data from Wenatchee, and we looked at variables temperature, humidity, and wind speed. And from this correlation table, we can see that there was a slight positive impact with the variables for Rocky Reach headwater elevation. However, with Rock Island, there was actually a slight negative impact with the variables. And then for some visual representation, we can see the slight positive trend line while looking at temperature and the headwater elevation for Rocky Reach. Overall, we found that weather data was not very impactful with our overall analysis with the headwater elevation levels. So for pricing, we took 5-minute interval pricing data from 2022 to 2023, looking at representing the marginal energy costs in dollars. And we actually found that there was a correlation evident with the Rocky Reach discharge rates. Our interpretation of the scatter plot shows a negative trend line where the discharge rates are high. However, the pricing is low from the $0 to $100 range. This represents high runoff season, where during this time, for example, if there's snowmelt, a lot more high volumes of water are going through the dams, which results in higher discharge rates. But we can also see that there is a slight positive trend line where the price is increasing, indicating that there is a scarcity in the market. Overall, we found that the pricing data really showed some interesting insights with our dams data.
Thank you, Ava. So in conclusion, as you can see from all of our results, you can actually see that PCA, or principal component analysis, did a significantly better job at finding results compared to the traditional model and the linear and the traditional model in our time series analysis. PCA explains about 99% of the variance compared to the traditional model only comparing about 19% or less. But the traditional model does really well when you want to look into the long term, but it only does fail when we want to look into real-time predictions. But that's where our PCA model comes in and excels really well, because it can highlight all the most influential features and of what's influencing the headwater elevations, and you can easily apply it to time series models for more accurate predictions and forecasting. Also, by adjusting our analysis to not only look into daily, but look into quarterly analysis, you can actually see how this gives insight to Chelan County PUD for looking into water discharge and electricity demand throughout the year. As you can see from the quarterly analysis, each quarter has features different variables. So by applying those specific features to the respective times of the year can potentially give Chelan PUD a better opportunity for dam operations and water discharge. And lastly, looking to our time series results, unfortunately, the relationship between headwater elevation and weather showed little to no relationship, but as you can see from pricing and discharge, you can actually see some insightful trends. Those noticeable trends can give Chelan County PUD insights for operational adjustments and strategic planning as they look for energy production and also look for market anticipation. Especially looking at times during high runoff seasons, which are around times of like May or June, they can anticipate more water coming into these dams, and they know how much water to potentially discharge, and also look into opportunities for how much they should be charging for electricity from their electric customers. So with that, for takeaways and limitations, the biggest limitations that we did come across doing all of our analysis was just dealing with the seasonality and a lot of variable change from just a lot of environmental changes. So just because of that, seasonality really limited our abilities to just forecast accurately more into the future. But as to move forward, if we were to have more time with this project, we decided as a team that potentially if we spent more time finding other data sets that looked into 1-minute observations, and apply those into our time series rather than just calculating mean averages or hourly averages, it potentially could have improved our results significantly. As you can see, we're always constantly getting means in all of our time series models. And lastly, potentially, if we already use the adjusted data set that features all the highlighted variables for headwater elevation and apply those to our time series, instead of using the whole data set, it also could have potentially provided more insight as to better dam operations for Chelan County PUD. So with that, we would like to thank everyone for being here today, but we love to really thank our sponsor, Chelan County PUD, especially Peter, John, and Carl for being great liaisons throughout this entire process, giving us the resources that we need to be successful. Big shout out to Dr. Slaughter and Dr. Mendible for being great advisors, making sure we're accountable for all of the work. And lastly, I'd like to give a big shout out to the Project Center here at Seattle U for giving us this opportunity. With that, we'd like to conclude our presentation, and we'd love to open the room for questions.
Maybe wondering about the 16 principal components. Seems like an awful lot that you can explain variance. You have a huge number of variables like that. Did you consider, or did you look at, playing with reducing the number of variables and seeing, was there covariance between variables that you were able to eliminate and yet still, explain the variance in the model?
Yeah, we try to do other feature selection methods too, but PCA doesn't remove the features and it transforms the features into principal components, right? So each principal component is like a combination of other features so that we don't lose any data which is important for our analysis, because if we are doing just averages or considering only few variables, the results are not that great. So to not lose the data and still perform well, that is why we use the PCA. Actually, headwater elevations are kind of constant over the years, so I don't know if there are any droughts or something like that, because the weather data we had, it has temperature, wind speed, and humidity, and none of them showed extraneous, any of the extreme values over these 5 years. Yeah, we found the coefficients of these values. So I said one sentence like Rocky Reach mostly depends on Welch Dam, not compared to NTR and Chelan flow. These we found from those PCA components. They show much variance in the Welch Dam discharge because there is a lot of water coming from Welch Dam, and comparatively NTR and Chelan has very little flows. Those are the river flows, and Welch Dam, they have a lot of discharge coming. So using PCA, we found that, okay, we shouldn't average the values. Instead, Welch Dam components are having much more coefficients compared to the Chelan and NTR. If it is like 0.4 and Chelan is like 0.002.
guess only one is working. Is that good? No, sorry, can you see the right presentation? On Zoom? Oh, it says, sorry. I don't know why it's, hold on, let me just. What do you mean? It's good? Okay. Which one of these was the good one? Okay. You guys have you ready? Okay. Wait. Okay. We're going to be starting our next presentation. So this is our second MSDS team that has to do with a public utility. So please, let's give a round of applause for our PSE team.
Hello, everyone. My name is Samiksha. Emma Chong and I are in MSDS 24.4, and we're here to give a presentation on Green Power Program churn analysis and engagement forecasting. As a brief introduction, all of us are in our final year of Masters in Data Science, and for our capstone project, we worked with Puget Sound Energy. Our sponsor liaison was Graham Marmion, who is a data scientist at Puget Sound, and our faculty sponsor was Dr. Slaughter. In this presentation, we will walk you briefly about the organization Puget Sound, how our project fits into their goals, and our results, as well as some of the limitations. To begin with the introduction, Puget Sound Energy is one of the largest utility companies in Washington State, and they serve over 1 million customers, and their mission is to provide affordable and reliable energy to all its customers. They source their electricity from different sources, such as coal, hydropower, wind energy, etc. And they're increasingly focusing on green energy because they want to support the Washington to reduce the greenhouse gas levels 30% below what it was in 1990s. And it also has the aim of reaching net carbon energy by 2045. One of the programs that they have in order to serve this goals of there is a Green Power Program, and which is the project that we're working on. My teammate Chong will now go into the project and how we fit into the scope.
Thanks, Samiksha. Yeah, just a little bit more about what the Green Power Program is and why we are pursuing this project. The Green Power Program allows PSC customers to offset their carbon emissions by opting in for clean energy. They can buy green energy credits, which are purchased by PSC externally, and it's cheaper to buy in bulk, which is really important to forecast that 6-month demand so they can accurately match the actual demand of customers, which comes to the big issue of them struggling to predict this demand in 6 months in advance. So this is where we come in, where if we're trying to predict an accurate 6-month demand that will match actual demand, this will reduce the overall cost of overestimating how many credits to buy and lower the cost for customers overall. And we have 2 main goals for this project. The first one being to accurately predict a 6-month demand for the number of credits to buy. And yeah, this overall will reduce purchase surplus, reduce the cost for customers, making it more affordable and attractive to newcomers. And the secondary goal is to identify key factors that influence engagement. And by doing so, this will allow PSC to kind of tailor their offering and outreach strategies to make the program more attractive and improve retention rates. Now, the data set that we'll be using is provided by PSC. It contains 10 years of simulated data with variables like enrollment dates, unenrollment dates, monthly energy consumption, and customer location at a census tract level. We've also added more census data like an individual's education level, income, and age. Now we had to aggregate this to a census tract level to merge it with PSC data to continue with our analysis. They weren't able to provide us with individual level data. And to address the issue of what factors influence engagement, we decided to create a logistic regression model. And this model essentially is a decision maker to predict the outcome of 2 possibilities, which in our case is whether someone will enroll in the program or not. It will not give us a definite yes or no of someone enrolling in the program or not. It gives us a likelihood of participation. So it will spit out a percentage that will tell us, based on these factors, there's a percentage that this person will enroll in the program based on the data that we used. And the logistic regression model creates a confusion matrix, which plots the predicted outcomes from our model with the actual outcomes in the data set. We achieved an overall accuracy of 69%, and it was better at predicting customers who was able to stay within the program with an accuracy of 74% compared to the 60% for customers who left. So this can suggest that the data set is better aligned with customers who stayed within the program and kind of struggled to find patterns with customers who left the program. And 69% is a strong prediction. However, we believe that by analyzing this with more granular data, like individual data on an individual level can improve performance and accuracy. So what factors actually influence engagement? There were 3 statistically significant variables that emerged. Average age, start service date, and enrollment date. There was a negative correlation between participation and average age, which means that younger customers are more likely to leave than older customers. And there was a positive correlation between participation and start service date and enrollment dates, which tells us that people who enrolled recently are more likely to stay than long-term customers who have been with PSC for a while or have been in the program for a long time. Oh, sorry. I wasn't done. So this, even with just these 3 statistically important, significant variables, it can help PSC kind of tailor their targeted communications towards the younger demographic to kind of make them stay with the program for a little longer. And the reason behind why recent customers and people who just enrolled in the program could be due to initial enthusiasm or just similar alignment upon signing up. Yeah, and I'm gonna hand it off to Samiksha to talk about the next model.
Thank you. So another goal was to see if we can predict the demand for green power program. As we'd mentioned, PSC externally sources this credit. So if they're able to accurately predict what the demand would look like for the next 6 months, they could make a more cost-efficient decision as well. And our solution for this goal was to create a time series forecasting model. What a time series forecasting model does is it has an output variable at the fixed frequency of time. So whether it's monthly, weekly, annually, etc. And what we did was to calculate the total green power program usage per month. And we are using this information to kind of predict what next 6 months would look like. Within the time series forecasting model, we specifically chose ARIMA model. ARIMA model it kind of looks into the relationship between the present value and the historical values to see if there's any short-term dependencies or patterns that we can extract to forecast for the future. And this model is highly flexible, adaptable, and it is easy to interpret as well. Moving into modeling, we experimented with different kinds of parameters within the ARIMA model, as well as a base naive model that just kind of predicts, that assumes that the demand remains the same as a evaluation metrics. And when you look at this graph, you can see that the blue line traces our training data, and then the red dashed line shows what we forecasted the value to be, and then the green is the test data. As you can see with the red shaded, our model was able to predict within the 95% confidence interval. And so we use this model to kind of forecast the next 6 months. When we look into the ARIMA forecasting model, the blue line traces our training data, and then the red dash line shows what we forecast the next 6 months to look like. Our model was kind of able to capture the downturn in the demand for green power program that you can see. And we hope that this kind of information supports PSC in their decision-making for when they buy credits in the future. Now I'll hand it over to Emma to kind of discuss the kind of patterns we saw in customer participation using Power BI.
Thank you, Samiksha. So we performed some exploratory data analysis to learn more about the Green Power Program customer base. And to do this, we utilize a tool called Power BI. Power BI is a Microsoft platform that allows for easy data manipulation, data analysis, and data visualization. So our first goal was to estimate customer demographics in the Green Power Program. As previously mentioned, we had customer location at the census tract level. So for each customer, we pulled in aggregated census tract level demographic data, and then we used Power BI to analyze and visualize this data. So this top visualization here is showing the estimated proportion of customers by their racial identity. We see that the largest proportion of customers identify as white, with the second largest group being customers who identify as Asian. We also estimated the proportion of adults with a college education, the median household income, and the average age of customers. Now, our goal was to compare the demographics among customers who are currently enrolled in the Green Power Program compared to customers who unenrolled to see if demographics are associated with unenrollment. And we found almost no measurable difference between these groups. Now, this could mean that it's possible there is no true difference in any of these metrics between those groups of customers, but what we think is more likely is that the census demographic data is aggregated at too high of a level to be fine-grained enough to detect these differences in demographics between customers. So we also performed some exploratory analysis looking at trends in customer participation in the program over time. And the first thing we evaluated was the Green Power Program churn rate. The churn rate is the rate of customers leaving the program to joining the program. And so we see that in 2023, we reach a churn rate of 1, which means that for every new customer gained, 1 existing customer leaves, resulting in a stable and unchanging total customer population. However, if the churn rate continues to trend upwards, then past 2023, we are going to see a shrinking customer base. Additionally, we calculated the number of customers who are unenrolling from the Green Power Program, but continuing service with Puget Sound Energy. This was a particular metric of interest because these are customers who are deciding to leave the program, not because they are leaving the Puget Sound Energy service area region, but for another reason. And so we see that the number of customers leaving but continuing service peaks at 2020 during the pandemic and has been sharply but steadily decreasing since. We had several limitations in this project. The first was that we were working with a simulated data set to protect customer privacy. So we were building all of our models on this simulated data, testing it on the simulated data, and then handing them off to Puget Sound Energy and having them test the models on the real data to make sure that we were not overfitting our models to the simulated data and that it was performing similarly well on the real data. Additionally, we only have customers who are currently enrolled or previously enrolled in the Green Power Program. So this really limited our ability to compare to customers who have never joined the program and understand the differences between those customer groups and why people may be choosing to engage with the program. As previously discussed, we believe that our census data is aggregated at too high of a level and is an imprecise estimate of customer demographics. Additionally, the pandemic disrupted patterns in customer energy use, and so we had to make sure that our time series model was recalibrated to new trends in energy usage. Additionally, our model cannot account for any external factor influences. For example, if there were to be a public policy in Washington that affects customer energy usage, our model would not be able to predict or account for that. And lastly, we have no seasonality in energy usage data. So for each customer, we were given their average monthly usage across the entire span that they were in the program. However, we know that energy usage fluctuates greatly throughout the year, and our simulated data set did not reflect that. In conclusion, we detected a stabilizing customer base as of 2023, with a projected slight decrease in demand for the Green Power Program in the next 6 months. If Puget Sound Energy is interested in further exploring how demographics are associated with customer enrollment, we recommend that they do some of their own data collection or look for data sources outside of the census. And we recommend implementing communication strategies and initiatives to improve retainment in younger customers and customers who have been with Puget Sound Energy longer. A huge thank you to Graham, our sponsor with Puget Sound Energy, who is here today, Dr. Slaughter, our faculty advisor, Dr. Mandile, our capstone instructor, and Macklin Hamilton, and the whole Project Center team. And at this time, we'd love to open it up for questions.
That seasonal fluctuation data in terms of the technical details? Would it be just a hot swap or?
The question was, if our simulated data recommended seasonality, how would our models have changed? We actually built our model to account for the seasonality. That's why we chose an ARIMA model, because it's particularly good at detecting seasonal trends and predicting them. So we did train our model on non-seasonal data, but when we handed it off to Puget Sound Energy, they trained it on seasonal data and it predicted on seasonal data, so it didn't need any adjustment. The question was if we had any information regarding location. We had customer location at the census tract level. So I'm not sure exactly how large a census tract is, but it's basically, I think, like a neighborhood. The question was, did we have measurements on how close the simulated data was to the actual data? The simulated data was handed off to us by Puget Sound Energy, but we discussed with our sponsor and he said that it matched the real data in all of the metrics checked, like, I don't know, averages, standard deviation, et cetera. So we didn't have any of those metrics, but it did match the behavior of the real data.
So now we will have a 15-minute break and we'll come back at 3:15. Again with our MSDS presentations. So as was stated before, but I'll state it again in case you're just coming for the first time, this work is a culmination of 2 quarters of really hard work, both from the student teams and from the sponsors. So I'm really excited to present the last 3 MSDS teams. And first we will have our National Oceanic and Atmospheric Administration team come up. Let's give them a round of applause.
All right. Hello, everyone, and welcome to our capstone presentation, where we are doing a meta-analysis of the Elwha River water temperature regime. So my name is Malia, and I'm joined with my teammates June, Anna, and Taylor. And I will start with a little bit of background about our sponsor and the data itself. So our sponsor, as you know, is NOAA, who have 3 main goals in their mission. They're focused on scientific research of climate, weather, oceans, and coasts. Public service through communication and dissemination of knowledge, and finally, coastal and marine ecosystem stewardship. So our data comes from the Elwha River, which is located in Olympic National Park in Northwest Washington. And as a bit of background about the Elwha, it's home to species of salmon, which are keystone species and also important very culturally in the region. Between 2011 and 2014, two hydroelectric dams, the Elwha Dam and the Glines Canyon Dam, were removed, allowing salmon to access the remaining 90% of the watershed for the first time in over 100 years. So NOAA and their partners have been studying the Elwha for over 20 years, which is where our data comes from. And there is a growing interest to find out the effects of dam removal on salmon development. So you might be wondering why we're focusing on temperature. Temperature, besides being an important indicator of freshwater ecosystem health, it is important as climate change continues to warm waters. It is important to sort of characterize the thermal regime. So in addition to that, dams are also known to influence water temperatures, and salmon are very sensitive to these temperature variations, and as it dictates or it can influence the duration of life cycle stages. So more motivation on our project and where we sort of come in on this. So first, we are sort of looking at the missing values in our temperature data. So we can see from this histogram that the vast majority of sites have 80 to 100% of data missing. And this makes it very difficult to analyze the data over time and look at trends. Curious about where exactly the data was missing, we saw that as the years go on, and more recent years, as more systematic efforts to continuously track temperature data have increased, we see a sharp decrease in the number of missing values, whereas the more historical sites exhibit much larger number of missing observations. Secondly, we know that data collection is very expensive and difficult. Besides the Elwha being mostly inaccessible by car, it is also 45 miles long and has over 2,100 feet of elevation gain, making navigating the terrain very difficult. The temperature loggers are also manually placed and also manually handled in order to collect data from them. So a trip to sort of either put in or collect data from these temperature loggers could easily take days or weeks. Third of all, the visualizations also lack a time series approach. So this is a screenshot of the current data, the Elwha data that NOAA Fisheries has. And we can see from this middle plot right here that on a month basis, each of these lines represents a different year, a different year's temperature trend. So it's not currently represented as one continuous time series from 2000 all the way to the present day. So given these problems that we identified, we created some questions to aid in the development of our project. In order to address the gaps in the data, we ask ourselves how we can accurately reconstruct the missing data given the magnitude of missing values. Because data collection is expensive and difficult, we ask ourselves if we can group sites that are similar in order to limit the interaction that people have to have on the river and optimize the locations. Third, to address the visualizations lacking a time series approach, we ask ourselves how we can display the data to a public in the time series in a way that allows our sponsors to expand on the work we've done. And now I'll pass it to Taylor for the first part of our solution in data reconstruction.
As Malia had said, due to a lot of complication, and even with our best effort, this is a logging site at the Indian Creek, a tributary of Elwha River. We still have like missing periods of data, which could be more than a year. And with this type of wave in temperature data, it is really inappropriate to do like linear interpolation for missing data treatment. So we found a technique to deal with this, which is called compressed sensing. In our case, it is built upon the idea of frequency transformation. The original waveform is comprised by multiple contributing frequency, and each frequency have their own significance to the original structure by the amplitude. After breaking down into frequencies by using only the dominant frequencies, we can reconstruct like the major structure of the original signal with some error. So with that, we tend to evaluate this technique using our first 3 years of data with sampling size 30%, and then extrapolate any underlying patterns through time to recover this missing data period, and then use these currently data to evaluate the model. So after plugging it in, we found that the dominant frequency in this 3 years period have their cycle of 369 days. And they have the highs during June to August, and the lows during December to February, which is aligned with a general perception of temperature seasonality. The mean absolute error for this technique is 0.75 degrees Celsius. After being interpolated through time, we could reconstruct the missing data with mean absolute error of 1.43 degrees Celsius. This is higher than the interpolation one. One observation is at this 2013 and 2015 period, there's some natural spike in the summer that the model cannot account for. The model actually fluctuate through the mean baseline, and it really not account for like any outlier. Some more limitation that we found out with this technique is that it could not capture the annual seasonality of the temperature if the training data is less than a year. So with this technique, with this newly reconstructed data, we use it to our further analysis of site similarity.
Okay, after we finish cleaning and reconstructing the data, we are gonna group them. So the way we group them is trying to extract the numerical properties of the time series we reconstructed, like the annual mean temperature and then the annual variance temperature, throw them into the K-mean model, and then sort and group them based on their numerical similarity. How do we think? Why do we think that we can do that? Is because this is one of the plots from two of the closer sites, ICO1 and ICO2. Then it looks like just one plot is because they are overlapping a lot, and it shows like a purple color. They are actually coming from blue and the red color plot, and they have a correlation of up to 0.92 out of 1. Okay, here's the results after we do the clusterings with the top, side, and the front view. This is the first group of interest where they are near the river mouth, and where the river meets the oceans. That tends to have a warmer temperature and stable temperature fluctuation. The next group of interest is the green clusters, where they are located at higher ground than the other sites. The third group of interest is at the middle river, where they are also kind of apart from the other sides. And this group and the last group that show us that the elevation actually takes a great part of this road to determine the river temperature. Okay, after we have all the clusterings, we have to determine what are the spatial features that could affect the river temperatures. We are using the spatial covariates given from the sponsors. There are 77 spatial and environmental factors such as the air temperature, drainage area, tree canopies, precipitation, and elevations. This is the results we get after we use the predictions model. And we can see that the elevation actually takes most of the parts, because out of these 10 big features, there are 3 of them. They are minimum, maximum, and the mean smooth elevation. Besides, the distance from the ocean is also another part. It doesn't mean that the other features is not important. It's just that the amount of sites that we are investigating is not that much that we can use them to predict the features' importance.
Okay, so now I'm going to talk a little bit about our data visualization solution. So when we were deciding how to visualize the data, some of our important considerations were cost and then also being able to hand it off to our sponsor after we were done with this project. With all that in mind, we chose to use Shiny in R. Shiny is a package that lets you do dashboard style visualizations in both R and Python. Our sponsors had previous familiarity with Shiny and R, and it's also free and open source, which is a big bonus for it over solutions such as Power BI or Tableau, which are both licensed software that will cost our sponsors money in the long run. We also use a host of other packages to kind of assist with the development that are listed here. We can get into some of them if there's any questions about any specific one. And then the data that we fed into the dashboard included the temperature data, the geographic data, and then also the interpolated data that my teammates talked about in their previous sections. And then I hit the wrong button. Okay. So this is just a quick video showing some of the interactive features of our dashboard. So you can select the different sections of the river you want to look at. You can select a specific site. You can choose to see the interpolated data or not. And then you can also filter based on a specific time series. So say you want to look at 2011, 2018 onward, you can choose to see just those. Then we also have a page that allows you to compare different sites to each other. So you can filter and then see again the just straight up temperature of the sites. And then you can also see aggregated statistics such as mean, min, and max. And this is again, just kind of a quick recap of some of those features. And so some limitations of our dashboard solution. It's not currently publicly hosted. This is something that we're working with our sponsors on. We ran out of time before Projects Day, but this is a big goal of ours because of that communication and education piece. There's no live data connection, so the data came to us as a CSV format. So as new observations are measured in the field, we will have to manually update the dashboard because the data is not currently in any sort of database or anything like that that we have access to. We had to do a lot of custom data transformations for the dashboard because of the different visualization packages we used. So we have kind of a script that we can use to transform the data and then feed it into the dashboard, but it's something that we're kind of working on refining, so it's really easy to hand off to our sponsor. And then also because of all those transformations we had to do, it was initially really slow depending on whose computer you were running it on. But we've changed where the data get loaded and how the transformations happen. We're still tweaking it to kind of really make it fine-tuned, but that is a limitation of it right now. Okay, and then just kind of talking about some conclusions going back to those initial questions we asked ourselves. We asked ourselves, how can we accurately reconstruct the missing data? Compressed sensing allowed us to really capture that kind of time series approach and then the different fluctuations, especially seasonally, in the data. And then can we group similar sites? Yes, we can. We found that we can cluster some of the sites together and that can help guide future logger placement since we can see how similar there are some sites on the river. And then we asked, how can we display the data to the public in a time series? We made an R-Shiny dashboard with interactive features that should allow NOAA to communicate better with their stakeholders and allow them to do greater analysis on an exploration of the data over time. And some just kind of bigger picture takeaways here. This definitely was a lot about project management, 2-quarter project, working as a team together, trying to figure out how we're going to organize ourselves and communicate well with our sponsors. Solution evaluation, especially for the dashboard solution, we had to talk a lot about pros and cons and cost evaluation. We kind of wanted to go with Tableau or Power BI initially, but because of the cost, we decided to go with R. It took us a little longer to develop it, but ultimately it'll be a better solution for our sponsors. Communication in terms of data visualization, report writing, emails, and all that kind of good stuff was a big piece of this as well. Resource allocation in terms of just trying to help our sponsors guide how they can best use their limited resources when they're out on the Elwha. Data simulation and reconstruction to get a better picture of the time series data, and then applying new methods. So especially with the signal processing and compressed sensing, that's something that's been developed like since the early 2000s. And so we know data science is a really rapidly evolving field. And so we were able to take this kind of newer methodology and apply it to our project. And that's something that'll definitely serve us well in the future. And then we just want to say thank you to our sponsors, Sarah Morley, Dr. Amy Fullerton, our capstone faculty advisor, Dr. Ariane Mendible, and then the Seattle University College of Arts and Sciences Project Center and Macklin Hamilton, our project coordinator. And any questions? like as far as the dashboard, as far as the modeling? Dashboard maybe depending on how the data set is formatted. I think we could do some customizations to get it in there, but it might be a little tricky just because we don't have like super standardized data format. But it does basically just take temperature versus time as an input. So that should be pretty generalizable, but things happen. And I'll let my teammates address the other question.
For the data reconstructions part, you can, yeah, that applies because these are numerical features and just need some modification and then you can transfer everything to over another, yeah, values.
That was kind of my question too. If that's more specific, so there is, USGS has temperature data that's kind of hard to get to. And I'm wondering how much potential there is to this preserve all of their data straight. So is that something, could you handle like 100 times as much points?
If the computation power is strong enough, yes. And another constraint is that this compressed sensing, so far, we think that it can only apply to some data that has the stationary and the auto-relation properties. Yeah.
So when you the compressive sensing model, you're doing it separately, or you're doing it collectively? In other words, did you ever consider spatial correlation?
Yes, I do. That's why the first step we do is by cluster them based on the spatial features. That's why we are picking just 10 top optimal sites because there's based on the limitations of how many loggers we have to collect the data, which it was about 25. We choose 10 based on the spatial features, and then we are recommending that 2 for each clusters, and then 5 for the new interested locations for them to collect the new data. We do try with different transformation, but we do not have enough time to get the results from it yet, but it works for different kind of transformation.
Yeah. It was not read. Okay, our second presentation of the session is with the Washington Brewers Guild. So let's give them a round of applause.
Ready? Right. Hi, everyone. My name is Kenzie, and I'm here with. I'm Tanisha Gary.
Justin Jerry.
And our project is on the craft brewing industry in Washington State. Okay, it's working. It's working. Our sponsor organization is the Washington Brewers Guild. They're a nonprofit organization dedicated to advancing the interests of craft brewers in Washington State. They have 3 main areas of work. The first is advocating for craft brewers at the state legislature and other governing bodies. They also provide educational forums for craft brewers, and then they connect craft brewers to each other as well as to other folks in the industry, such as suppliers. Their mission is to foster a thriving industry for the craft brewers while also creating quality and choice for beer consumers. I'm going to pass things over to Yenting, who's going to talk about our project scope.
Thank you, Kinsey. So in our project, the main scope that we are striving for is trying to understand the landscape of the Washington State brewery industry. And throughout the previous years from 2017 to 2022, we have seen growing trends in production, and we like to go further into understanding these production trends and understand where the breweries were. We study the locations and where their brewery production has taken place, and also we developed a model to specifically predict how the pandemic has affected the brewery operations in the year of 2022. And then we also build a model to forecast the production trends. So now I'm going to pass to Alicia.
Thank you, Enting. So to achieve that, it required extensive data processing and cleaning for our analysis. For that, we have gathered data from various sources, including from Brewers Association, Google Maps for geographic location, Open Brewery Database, social media, and Untapped. It's an application which shows a list of breweries and its ratings. We have also accessed production data from Washington State Liquor and Cannabis Board to analyze trends in beer production, beer styles, and brewery closures, and also from Tax and Trade Department for getting any quarterly data. We've found some missing data. So for handling that, we have excluded breweries with more than 3 consecutive missing months. We have addressed openings and closings in 2022 by setting production to 0 before and after these events. For gaps within the year, we have used linear interpolation. At the beginning and end of the year, we have applied backward and forward substitution to fill in the missing months. After getting all this data ready, we have started our analysis by first looking at total and mean beer production data. So in 2022, the total production peaked at 60,000 barrels in August, with average monthly production also peaking at 170 barrels within the same month. So this data clearly shows us the seasonal trend during summer, which with production being highest during summer, which highlights the importance of summer for brewing industry in Washington. Looking at the top 10 producers. So we found out that the top 10 producers remain consistent from 2017 to 2022 as well. So from which Georgetown Brewing Company increased its production by over 40,000 barrels, raising its market share to 35%, while Reuben Brews made a significant jump from outside the top 10 in 2017 to almost to the 4th place. So overall, the top 10 producers saw an 8% increase in the total production, which shows us the industry growth despite the pandemic challenges. So as we have seen a seasonal trend during summer in our previous analysis, we wanted to explore more about the seasonality in production. So we found out that the quarterly production data reveals a seasonal shifts with peaks in Q2 and Q3 exceeding 160K barrels. Here, the COVID-19 impact is very clear. If we look here at the Q2 for 2020, it just dropped by over 130K barrels and increased by 3%, surprisingly, in Q3 for 2020 compared to 2019 Q3. And in Q4 for 2020, we saw the lowest production within our data set. However, in 2021, it showed an uptick in production ranging from 135K to 190K, which shows the industry's resilience and recovery. So after looking at all the seasonality in production and the different trends in this industry, we wanted to know how the beer sales were during all these years. So coming to the beer sales, we got the result that before the pandemic, the keg sales dominated the market. However, there was a decline in 2019 with the keg sales and a major drop in 2020 due to the pandemic. So during this period, breweries started selling bottles and cans. If you see here, they started selling bottles and cans, increasing by 18%. So in 2021 and 2022, bottles and cans started to decline, while keg sales began to rise again, bringing back the pre-pandemic consumption patterns. So now Justice will be talking more about the brewery production by legislative district and other findings more in detail.
Thank you, Hanisha. So Washington has 49 legislative districts, and the production by legislative district map here shows that the leader here is legislative district 34, which mainly covers Southwest Seattle at 142K. It's also good to know that this is the legislative district that is home to Georgetown's Brewing, which is the largest producer of beer in the state. Followed by other regions, as we can see there, Bellingham, Central Washington there near Yakima, and also notably there is another coverage there, which is mainly Northwest Seattle. When we look at the count of breweries by legislative district, here we note that the leader here is legislative district 3, which mainly covers the city of Spokane, with 21 breweries in that region. Again, matching the production by legislative district there, we see that legislative district 34, which covers Southwest Seattle, is also among the top 3. When we look at these two, we put these two measures together, the market's a bit clearer that there are some legislative districts that have few large breweries, and then there is some that have many small breweries, which highlights the dynamic of the region. And this made us curious about the overall location of breweries across the state. So next we look at the location of these breweries in 2022. That's how the map looks like, and the map on the right shows us where these closures occurred. We see that there are about 500 breweries that are operating in 2022, but 7.5% of those have since closed, which corresponds to about 30 breweries. However, this closure was not uniform. There was differences, and we see that King County is the leader here with about 10%, followed by Spokane County at 7%, and some counties like Clark County has below average closure rate at 4%, which somehow relates back to the count by legislative district in terms of the number per legislative district corresponding to this closure. But now we wanted to understand more what is causing these closures. So I'm going to invite Ying Ting, who is going to talk about our brewery closure model.
Thanks, Justin. So in our model for brewery closures, we are using the support vector classifier as our supervised classification algorithm. And using the algorithm, we're able to capture the nonlinear relationship within the data set. And that's enable us to learn about the important factors that affects the longevity of the brewery operation. So here we can see from the right graph that having most of the breweries that closed in 2022 were less likely to be members of the Washington Brewers Guild, and they were having lesser community engagement with the on the Untappd, and also has lesser ratings. And one fact about during 2022 is that they're also in areas where there are more COVID cases. And finally, they were having less years of experience, less years of establishment as in aggregated statistics. So now I'll pass to Kinsey to talk about forecasting model.
Thank you. So we also wanted to understand how the industry might grow over the next several years. And so to accomplish this, we developed a forecasting model looking at statewide quarterly beer production. The model that we selected is known as SARIMA, and this model takes previous values as well as previous error or white noise in the data to help predict future values. It also considers seasonality within your training data set, which, as Hanisha noted earlier, our quarterly production data is seasonal. So the first thing that you have to do when developing a model like this is make sure that your data has no trend, for example, upward or downward within it. This is known as being stationary. And our data was not stationary. So the first thing that we did was apply a box-box transformation. And essentially this just makes your data normal. It removes the trend and essentially makes it stationary and ready to use for forecasting. The next thing that we need to do is look at the lags in the data. So this is the number of backward steps within your data set. So if we're thinking about quarterly data, 4 lags would be the same quarter year over year. So quarter 1 in year 1 versus year 2, et cetera. And then 2 lags would be every other quarter. So like Q1, Q3, Q1, et cetera. And so to kind of understand what lags are important in our data for predicting the future, we look at autocorrelation plots. And if we see the one over here, we can see that lags 2 and 4, like I described, are significant. Their spikes dip below or above the kind of light blue line in there. The lag at 0 is just the data against itself. So we don't consider that it's always going to be a correlation of 1. And so what we do with that is we create several different types of models that consider these different lag values, and then we compare the performance of them. We compare the performance using this AIC value, and that's just, it's a measure of model performance that also makes sure that your data is not overfit. And we selected our model based on which one had the best or the lowest AIC value, and we will see that on the next slide. So this is the model that we selected through that process. If we're looking at this plot here, the first line is our training data. So this is the data that we built the model on. The yellow line between 2022 and 2023 is our test data. And then the green line above it is our forecasted data. So this is the estimated data based on our model. And there's a couple of things that we can pick out from here. First is that our model did seem to capture the seasonality of our data set. It's mostly following the same kind of pattern as our test data. But the other thing to note is that our estimated data is higher than our test data. And our model actually forecasted an increase in annual production of 35% between 2024 and 2029, 5 years later. But as we can see, our training data has a bit of an upward trend, and that did not follow through in the test data in 2022 and 2023. And so our model might be overestimating these values by a little bit, but they do capture kind of the trend that we saw in our training data. So it's useful in that, but we'll see if the market continues that upward trend or if it kind of plateaus from here. So now I'm going to pass things off to Justice, who's going to conclude our presentation.
Thank you. So having collected data from various sources which were unconsolidated, which was the biggest problem in this case, we conducted a comprehensive analysis and developed 2 models. We determined that there were almost 500 breweries operating in Washington State, but 7.5% of these have since closed. We also noted the urban clustering of these breweries across the population centers like Seattle, Spokane, and Tacoma. The other thing that we note from here is the seasonality in production, with peak production in summer, perhaps associated with high consumption in the warm months, as well as the change of BSO methods during the pandemic. We saw the uptick of the various BSO methods. And then most importantly, we also noted the most important factors that caused potentially could result to brewery closure, which had something to do with engagement, the years of operation, good membership. That means whether the breweries that we're considering here are members of the Washington Brewers Guild or not, as well as the impact of the pandemic itself. So looking at these things together and the work of Washington Brewers Guild, we believe that this would provide data-driven support to their legislative initiatives and community advocacy. But we also have a couple of strategic findings that we take from this study itself. One of them is adopting measures that support the smallest breweries, which could involve advocating for more business-friendly policies, encouraging collaboration through things like research and investment and Washington Brewers Guild workshops. The other one is diversification of sales channels. We saw how that crucial it was during the pandemic. This is something that brewers themselves could adopt. Also, when leveraging proactive measures such as the use of predictive models to identify at-risk breweries before closure occurs, and maybe they can somehow stay in the market. And lastly, we want to, they can also encourage customer engagement through platforms such as Untapped, which helps them to gain feedback from consumers, and they can incorporate this kind of feedback into their production and stay competitive. And yeah, this would really help in keeping them in business. That is it from us. We believe by adopting those measures that the industry will stay more resilient, adaptable, and generally stakeholders will be able to contribute to the overall growth of craft brewing in Washington State. I would want to thank Dr. Ariana Medible, our faculty advisor, the whole team from Project Center, as well as Daniel Olson, the executive director of Washington Brewers Guild, for your invaluable support and guidance during the undertaking of this project. That is it from us. We would be happy to take questions.
Elaborate a bit on how you collected and joined together the data from all the different sources, like do apps like Untapped have an API query, or do you have to break a website?
I can start and then pass it off to anyone else. So it was a lot of manual data collection. This whole project honestly was a lot of manual data collection. There's not really a singular source of information about all of the breweries in Washington, as well as like information about them and their locations, et cetera. So that was a lot of collecting different lists, comparing them, and then doing, honestly, like looking at their social media and trying to understand if they're even still open. So that was one part. And then our production data was also a little difficult. It was just in Word docs. So we kind of had to compile like months and months of data into a singular data set, clean it. There was a lot of missing data, things like that. And then for Untapped, they have an API, but it's not available anymore. And so Yenting developed a script that actually scraped the website to collect that information.
Yeah, adding to that, also we have found some, it's not duplication, but for one particular brewery, it's located in different locations, let's say in Spokane and Seattle and in some of the website, we found out that it's still existing, but we have to cross-verify with other websites as well, let's say through Google Maps and social media, whether it's actually open or closed. Some breweries are opened in only in few locations, whereas it's closed in some other locations. So we have to verify everything.
Not directly, I'd say, but we were also only looking at craft breweries. So it's of a kind of certain size. It's why Georgetown was the largest brewery instead of a large brewery that distributes nationally that I can't think of off the top of my head right now.
Yeah, well, we adding to that, we did find out different beer styles, like some of the styles, not only breweries but different alcohols. People who are consuming, we have all that information, but we didn't include all of that because our main agenda is to focus only on the craft beers, and also we couldn't get the entire all kind of alcohol style information or data for all the years. So we just included only the craft beers for now. I think all those kind of sales were included in our beer sales, the sales data that we have got, it all included in that.
So we didn't like break it out.
Yeah.
Because that data is not available, but like if a brewery is selling beer at Target or Chuck's or whatever, it was included in the data.
I think that was our time for questions, so let's thank our speakers again. Can you test the clicker? Okay, and our last presentation is going to be from our team working with CDW-G, so let's welcome them.
Hello. Hello. My name is Alex. Thanks everybody for coming. These are my teammates, Arthur, Gokula, and Akanksha. We worked with CDW-G to build the Gov Segmentation Automated Research Tool, and we will tell you about what that is in a moment. Okay, so a word about our sponsor first. CDW-G is a leading provider of IT technology solutions, so IT solutions to government agencies in the US, UK, and Canada. We specifically worked with the federal sales and business development teams who are focused on contracting with federal agencies. So the initial ask from CDW-G was to improve the federal market research process. The current process is primarily manual and requires sales and business development people to navigate multiple industry websites to find the information that they're looking for. To give you a better idea of how this works, let's pretend that we work on the federal sales team. We're interested in doing some research. We go onto Google, we open up all the websites that we think we might be able to find information on, and we start looking through them. One might have 100 articles, another might have 200, another might have 300. We also notice that some of these websites might have simple navigation tools to search by title. Others might require you to just click through each page and read the article titles manually. After a couple rabbit holes, your screen might look like the picture here on the slide, and I'm sure many of you who have done research can empathize with that problem. And as you already know, that can be quite time-consuming and ergonomically inefficient. Another issue with this style of research is that it makes it difficult to get a broader understanding of whatever you're researching, because bringing all that data together and analyzing as a whole can be quite difficult without technical tools. So given the pain points in the current process, we came up with these requirements for a new and improved process. The first of which is to aggregate all those articles from the websites that we were just talking about and store them. The next is that we want to analyze and display those articles in a way which is accessible to CDW-G. And finally, we want the new process to be repeatable. CDW has a lot of clients, and in order for them to maximize the value from this tool, they want to be able to propagate that to as many of their clients and agencies that they're interested in as possible. So in order to meet these requirements, we went through a lot of iterations of trial and error, trying different things with CDW-G. And the solution that we landed on was to build an Azure data pipeline, and that's going to aggregate all those articles like we just talked about and store them for further analysis. Then we used a Microsoft Power BI dashboard to take that data and transform it into market information that CDW-G can access with just a few clicks. And the idea was to build a one-stop shop for industry news, insights, and analysis.
Thanks, Alex. To prove that our solution is workable and scalable, we set out to implement it for 2 CDW-G clients, US Space Force, US Army. CDW-G gave us 3 websites for each of these agencies, and the websites with their respective titles is mentioned on the slides. Now we have set the foundation of the data source which we use. Let's talk about the development framework. To begin with, we used agile methodology to develop our project. First step was to do an iterative exploratory data analysis, followed by visualization of the scraped data. The main aspect here was the feedback from CDW-G, because they are the one who is going to tell us that the data sources we are going to use is going to have a business impact. Once we had that foundation laid out, it also helped us to build a continuous improvement as well as make sure that we are delivering our product on time. Now, let's talk about the Azure pipeline which we used. From no data to a dashboard was quite a journey. To begin with, we had no data with us when we started this project. So the first step for us was to scrape the data from publicly available websites. We used Azure Function Apps to scrape the data. These Azure Function Apps gave us feasibility to use scheduled refreshes. Now, no one has to manually scrape the data. It's all automated. After the data is scraped, we had to clean it. So first step for us was to remove certain stop words, and then you remove certain words which are not useful, such as army, military, that were not useful for the business at that time. Once we cleaned our data, we had to store the data. So we used Azure Blob Storage, And then this became our powerhouse for our text analysis as well as being consumed by our Power BI dashboard, which has polished visualizations. This pipeline not only helps us to streamline the process, but also make sure that the dashboard is dynamically getting updated. That's the USP of our dashboard. Let's talk about the dashboard contents. To bridge the gap between data science and business insights, we have advanced search capability, name entity recognition, key phrase extraction, sentiment analysis, and word count analysis in our dashboard. Each of these will be touched upon in the later slides, but let me talk about word count analysis. So we believe that word count will help CDW-G to understand what are the most frequent words in the articles. Here, the bar graph on the left will help CDW-G to find most frequent words along with the word count. And the word cloud on the right will help CDW-G to look at a glance view of which words are more frequent. Here, the word size corresponds to its frequency. Now I'm passing over to.
Next, we have advanced search tool. This tool is powered by unsupervised natural language processing, wherein users are prompted to enter a search query or a search string, nothing but set of words. Users can search for topics, web sources, publication dates, or author or industry leaders. We label this tool as Smart Search Assistant, as the query entered by the user is type agnostic. In the sense, user can search for combination of topics and web sources, or else web sources and dates, or maybe dates and author or industry leaders. Followed by, we have key phrase extraction. This AI-powered feature leverages advanced algorithms to quickly generate list of keywords based off articles selected. For example, let's say we are looking at, we are processing thousands of customer review articles, and we are looking for to identify common issues among the articles, or else recognizing the patterns in the feedback. There where this tool comes in handy, it helps us to quickly generate those keywords. And also, if we have more volumes of data in our database, this feature performs more effectively. Followed by, we have name entity recognition. This especially helps users to spend less time in reading articles word to word. We humans generally pursue any given line of text. Per se, Peter has lived in USA since May 2024. Peter, that's a person. USA place, May, it's a date. So we generally pursue, okay, this statement is talking about some person living in place at so-and-so date. So we call these categories as entities in algorithm, and this algorithm does the job for us automatically. So this is an exact output by NER. Here the person is nothing but an entity that is tagged with the word in the article. So persons can spend less time reading articles. They can just skim through the article and get to know the gist of what that article is talking about. And USA is GPE, nothing but geopolitical entity. Here, this entity is more than like 7 letters, so it just represents as 3-letter acronym, followed by date, money, and organization. Overall, this gives us a first good glimpse of what article we're looking at. Followed by have sentiment analysis. This really helps us to categorize the text data into sentiments, positive, negative, or neutral. Positive sentiment yields a score of 1, negative yields a score of 0, and average sentiment yields a score of 0.5. So by leveraging all these emotional cues, businesses can gain deeper insights into market expectations or preferences, allowing CDW team to tailor their future go-to-market strategies more effectively. While this feature is made available, it's not currently included in our current dashboard version. It might show up in upcoming dashboard versions. So I'll pass over to Arthur for having a look at the dashboard.
Thank you, Gokula. Now let's jump straight into our dashboard. As you guys can see, our dashboard is split into 3 main components. On the left-hand side here, we have what I like to call our navigations pane, where a user can start off by choosing an author of the article itself, the web sources that we have scraped, the date of article published, as well as some overlying topics that categorize these articles. We also have our AI-identified key phrases, in which we utilize Azure Cognitive Services to extract specific keywords from our article's contents. In our middle section here, we have our keyword search functionality, where a user can treat the search bar as a regular search engine. It would then summarize the summary statistics at the top to show how many key phrases, articles, and authors are showing up. And then you can simply select on one or multiple articles to aggregate our visualizations. Our visualizations here on the right, we have our word cloud, which shows the importance of some words for each article. We have the number of articles by source. And last but not least, we have our named entity recognition that Gokula was talking about. Let's think about a specific use case here. Let's say that I am wanting to learn more about Space Force. I would first glance over the navigations page. Let's look at the authors, and let's say we have no idea who these authors are, as you normally would. I would then look at the specific web sources. I would choose web sources that are tied to the US Space Force, and I would be more interested in articles that are published more recently, so I would choose those published within 2024. Looking at the key phrases, I'm interested in the expansion of networks, so I would type in the word network, and we would come up with these amazing list of phrases, and it's a bit blocked here, but let's say I choose the phrase communications network. This will come up with 2 articles of CDW's interest, namely because it teaches them that the US Space Force is currently expanding their satellite network infrastructure and has plans to expand their operations overseas. Clicking some of these articles will also show you the exact article contents itself, so you don't actually have to go to some of these article links to go back to the original article or even connect with some of the authors that create these articles. This will lead CDW to connect with other federal service integrators that will come up with a technical solution to then present to the government entity. Last but not least, in conclusion, the government segmentation automated market research tool will allow CDW sales team to minimize their efforts to conduct agency or industry research. Our dashboard will automatically aggregate hundreds of web sources that will keep CDW up to speed with the latest market trends. Keeping scalability in mind throughout the entire course of the Capstone project, we are allowing CDW to continue to add even more web sources in the future, which simultaneously increases the value of the tool as more data is added. This will lead to future go-to-market strategies and teaming agreements based on the enhanced velocity and volume of data that CDW receives. Our proof of concept is already currently being used by our primary stakeholder. Clinton Austin, who is CDW's business development executive, has found great utility and time-saving benefits with this tool, saving him within 1 to 2 hours daily in research. It was with Clinton's contribution to the development of this dashboard that we were able to tailor the design specific to CDW's use case. We hope that as more individuals within CDW learn about this tool and gain familiarity with its capabilities, that it would continue to provide even more value to the business. Last but not least, we would like to extend our utmost thanks to the CDW team, namely Rita Bruce, who is here with us today, Clinton Austin, Corey Stonehawker, and Robert Olive, for their valuable time and feedback over the course of the project. We would also like to thank our faculty advisor, Dr. Elio Zhang, Dr. Ariana Mendible, as well as the CLU Project Center for their continued support over the course of the Master's in Data Science program. That concludes our presentation. Thank you all for coming, and we will now open the floor to questions. These are just including free sources at the moment. They were specifically given by CDW based on their previous success with these websites.
Not, we haven't encountered such issue because each of the articles have their own privacy issues. So we found unique articles from each website.
These were mostly just text data sources, but we converted our data into tabular format in order for Power BI to be able to properly aggregate the data.
CDW-G was already using Power BI, so it was easy decision for us to continue using that.
adapt to other agencies or other resources?
I can speak to that more. I think as more data is added, especially at a larger scale, it would be optimizing the data engineering part of things. So we want to make sure that a dashboard is operating as seamlessly as possible. So visualizations have to be continuously updated, at a moment's notice, as well as have very easy dynamic interactions. So definitely building a stronger data engineering portion of that would be optimal.
Any other questions?
As of now, every day, like we can scrape the data, yeah.
I think it definitely depends on what the website we're scraping allows us to scrape. Sometimes we are scraping using HTML scripts, and sometimes we are scraping using RSS feeds. Using RSS feeds allows us to ethically scrape, and usually they give us a limited amount of articles to scrape, and we have to abide by those rules.
If not, we'll conclude just a minute early so we can go enjoy some refreshments at the poster session. Let's thank our speakers.